कोई पार्टिसिपेंट है जो नहीं,
किसी से जूम ज्वाइन कराओ बाहर से और एक बार ऑडियो टेस्ट करा लेंगे।
वो बाद में कर लेंगे।
नहीं अभी किसी से ना रिकॉर्ड पे जाएगा ना,
अभी रहने टाइम हो गया, टाइम हो गया।
स्टूडेंट बाहर से कर लेंगे।
ठीक है, अभी यहीं बैठा है
तो मैं अपने फोन से कर लेता हूँ, इसको कंप्रेस कर देता हूँ।
नहीं इतना, चलो अभी
इतना ठीक है।
There are few guys. ठीक है, हो गया। दरवाजा बंद कर। हाँ, हो गया ना? Yeah, good morning. Yeah, nice to see you all here in Aries, and thanks for coming all the way to Aries in these conditions. So I hope many of you had a comfortable journey to Aries and having a pleasant stay in this beautiful place, Nainital. Yeah, as you all know, Astronomical Society of India has completed 50 years of existence this year. So therefore, we are celebrating this landmark, and also we are celebrating 75 years of India's independence this year. So we call it Azadi Ka Amrit Mahotsav. So under this umbrella, it's our pleasure to welcome you all for this 4-day workshop on star formation studies in context of near-infrared instrument on the 3.6 meter Devastal optical telescope. So this conference and workshop is organized jointly by Aries and TFR and will have presentation related to star formation studies and near-infrared instruments. We will also have a half-day workshop to give participants an introductory tutorial to the near-infrared instruments which are mounted on the 3.6 meter telescope. And on last day, on the 4th day, we'll have visit to Devastal to see the upcoming or the facilities which are there in Devastal. So on this occasion, we would like to welcome Professor P.C. Agarwal, Chairman, Governing Council of Aries, who is associated with Aries in the beginning of when Aries came into existence. And he has a very significant role in the development of Aries from the initial days to this day. So he has been associated since last 15 years. And I would also like to welcome Professor Ishwar Reddy, who is a director of India 30-meter telescope project. And we would like to welcome Professor S.K. Ghosh, who from TFR, who has very vast experience in star formation studies, and he has interest in near infrared, far infrared instrumentation. Also, I would like to welcome Professor Sandhu Rastogi from DDT Gorakhpur University, and Professor Sandhu Rastogi has taught us during our MSc, and many of us, like Amit was also his student, and I also. So I welcome Professor Sandhu Rastogi to this conference. And I also welcome all the participants who are coming from outside and from Aries itself. And I wish you have a very pleasant stay in Aries, Nainital, and Nainital in the town also. And we hope that this conference will introduce new collaborations for our future work. And the new researchers will benefit from the discussions with the experts in various fields. And I would also like to thank Professor Dipankar Banerjee for his keen interest in this conference, and he has given total support for this conference, especially the extension of this conference hall. Earlier it was 60 capacity, but now it's around 90. So thanks for Dipankar for this help for extending this accommodation for all participants. And he has following this work since last 2 months, and it completed last week only. And I also would like to thank TFR for funding this conference, and the SOC and LOC members and volunteers and staff of ARIES for their continuous work. So with this word, I would like to invite Professor P.C. Arwal to give opening remark. Maybe we could
just turn and talk also.
I can, but I think I can. Yeah, stand there.
Stand there?
just stand there.
Please.
Yeah. So after getting up, you take a few minutes to settle down.
Okay, thank you so much. First of all, I would like to thank Professor Dipankar Banerjee and Chairman of the SOC, Co-Chairman of the SOC, for inviting me to this, giving some opening remarks here. I want to apologize that due to some physical conditions, neurological conditions, my, the speech may not be audible, may not be understandable to some people. So please excuse me if I'm not very clear.
This mic also.
Okay. So first of all, good morning to all of you. And I might like to just make a few remarks. So Professor Dipankar Banerjee, members of the SOC, distinguished astronomers from outside, Professor Ishwar Reddy. Is it noise?
Phone, sir.
This is an interruption with the phone, yeah.
Oh, my phone.
That's nice.
But, okay.
No, it's.
So I would like to say that it's a very timely workshop, or it's actually more of a workshop rather than a meeting, because you are giving tutorials and hands-on experience to the participant. So it's very timely because the two instruments which are going to be instrumental in observing in the near infrared, they are mounted and calibrated, characterized, and they'll be used extensively. So it's good that people get exposed to the nitty-gritty of these instruments so they can make use of it and make proposal and make use. Am I clear?
Yes, yes.
Okay. Now, the two instruments are, one is a TenSpec, which is a TFR, it is near infrared spectrometer, and second is TFR near infrared imaging camera, TFR Chem2. Now, TFR Chem2 is permanently mounted on the side port of the telescope, while TenSpec is at the axial port because it's a medium resolution spectrograph, which is sensitive to 0.55 to 2.5 micron range. So near infrared studies are very appropriate spectral bands for studying the universe in its infancy. Similarly, immediately after the Big Bang, there is a dark universe. Nothing is seen there because it is like a primordial soup where particles, all matter in form of particles. So when when it expands, the particles combine electrons combine with the protons, and then you have the hydrogen and helium, and you immediately the era of reionization starts, and first light breaks out. Okay, so at the time the universe is about few hundred million years old. So then galaxies start forming because of the fluctuations, density fluctuation, and you start seeing light, which is in the form of infrared radiation, okay, from the galaxies, early galaxies, and then protostars starts forming, and you can see the protostars and T-Tauri stars. So these kind of studies are best done from near infrared. Now I would like to bring a parallel that while infrared band, near infrared band is ideal for studying in universities infancy, galaxy in their infancy and formation years, and young stars, which are, again, very just being formed and getting condensed, and before they come to the nuclear, fuel burning stage. So these all studies are best done. So therefore, the infrared window provides an opportunity to study universe in its infancy. But on the other hand, if there are stars which are, we call neutron star, black holes, white dwarfs, which are the stars born in the catastrophic explosions like supernovae, and they have other extreme characteristic that they have very high density, 10 to 14 grams cc, very high temperature, and very high magnetic field. And they lose most of the energy in the form of energy to photons like X-rays and gamma rays. And most of you are aware that India launched a satellite called S2SAT, which carries 5 X-ray instruments and a UV-AIT telescope, and it has been used extensively. I'm very happy that it has been used extensively by astronomy community in the getting the data and analyzing, and they produce a lot of. In fact, I think more than 24 papers have come, not from just the people in the institutes, but from astronomers at ICERs, at IITs. In fact, many IIT students are involved, and ICER students are involved. So it's a it gave a boost to the astronomical research in colleges, universities, and I hope that similar thing happens with the DOT. As you know, DOT is a modern optical telescope. It's based on new technology, and the thin mirror of DOT, 3.6 diameter mirror, is supported by 69 actuators, and this you can trigger these actuators and just the shape for correcting for the wavefront. So you can get a very fine image, 1 arc-second kind of image most of the time, but 10% of the time you are able to get an image as good as 0.7 arc-second at the DOT because of the very good laminar flow of the air above the telescope. So one is able to produce very good quality science, and you know that India already is one of the best radio telescope in the world. It's called GMRT, and upgraded GMRT has a very fantastic sensitivity in the 100 megahertz to 1500 megahertz range. It gives it is sensitive of 10 microzansky. So you can do world-class science. So now we are fortunate, I think Indian astronomy community is fortunate right now to have 3 major facilities which can enable you to do the cutting edge science. So I hope that the full details of the kind of science which you can carry out, details of the instrument, how you should plan your observation, this all will be realized and better by your exposure to this workshop. So thank you.
Thanks, Professor Agarwal, for your praising words. Now I invite our director, Bimodal, to say a few words.
Good morning. I think it has been a pleasure for me to see so many people in this hall. after I took over the charge here. Unfortunately, things were not all in our favor to meet people in person. So the first thing is, I'm really happy that we're able to meet, in person, and then, share our ideas and so on. Thanks to Professor Agarwal for all his guidance all these years to this institute and even to me as well. It's quite amazing. I was told that I used to really follow this practice. First mail to read is the archive email in the morning, and still he continues to do that. And he keeps a track of, research publications, even at the preprint phase, even today. So I think that's the sort of guiding principle what we should follow. And he mentioned about multi-wavelength. So I'm a solar physicist. Actually, I did whatever 30 years back by embarking into multi-wavelength astronomy, for that matter. I think today in Indian perspective, we have that right platform. And as you rightly mentioned, one of the probably best world-class facilities in the radio, multi-wavelength, the UV and X-ray in space platforms, and the best probably, one of the best, telescope what we have in hand from this part of the globe. So how to effectively utilize them and going beyond the research institutions also. So this is again another big mandate for the government to involve university sector, the new IITs, new ISERs. So last 2 years, we have been working closely for more MOUs with different IITs. Our students are going to be registered in IIT. I was in ISER Kolkata just last weekend. So I'm really looking forward for this, larger participation of the community and using these facilities. These are national facilities. Be aware of that, and we are proud that Aries has, the opportunity to have one of the best ground-based facilities. And thanks to the TIFR team, Oja and all that, again, multi-wavelength, the best possible infrared observations you can do today. You have the site, you have the telescope, so the back-end instruments also need to be, adequately good for that. So again, thanks for coming. I think Saurav has, mentioned few names. I will not mention individual names, but I would really thank all my colleagues here, because this has been a difficult time and we have done some jugaad here. You see that just to expand the capacity of this, but I'm sure there will be challenges. You already see the noises. So please use this door also to go out. I mean, in practical terms, I'm just saying somehow we have to just expand it, because those two doors may not be the most suitable way of going out and coming in a large number. So I'm looking forward for your good. I will probably learn something by attending few lectures. Star formation is one of my old favorite subjects during my coursework period. Also, I'd like to mention that probably this is a subject area where Aries was really, engaging in the early phase of its life. And now with the advent of the infrared thing, that can be expanded to much deeper level. Incidentally, we are completing 50 years of Sampurnanand telescope, which has done this field extensively. Of course, Professor Ramsagar and most of his students, and subsequently all these people. So we're going to celebrate 50 years of Sampurnanand telescope in October. And hopefully the bigger star formation meeting will have 2 or 3 years down the line in a much bigger auditorium. So we are trying to, expand this place with all your help and participation. We'd like to take this institute to the next level. So again, thanks for coming. Please don't hesitate to contact any of my colleagues or even me if you find any, teething issues on practical terms. We'll try to address it as much possible. Thank you very much. Thank you.
Thanks, Dipankar, for the encouraging words. Now I will call our associate here, Professor D.K. Oza.
Okay, so very good morning to all of you. And it's my great pleasure to welcome you for this conference on star formation studies in the context of NIR instrument on 3.6 meter DOT. And this is jointly organized by Aries and TIFR. And as Saurabh mentioned that we are celebrating 50 years of ASI this year. And to celebrate this landmark, I think this is the first workshop under ASI 50. And it's really a good occasion where there are two pillars of ASI president and ASI secretary, both of are here there. So I think it's a best occasion to celebrate this conference. So first of all, let me thank all the participants on behalf of the Scientific Organizing Committee to welcome you for this conference who could come from different parts of the country. And thanks a lot to all our senior colleagues who could actually able to make it and come here for grace this occasion. And the best part of this conference, I was seeing the participant list, almost like 65% of the participants are student and postdoc, and that is what was one of the goals of this conference. And as you see, this is the third meeting on star formation. So the first meeting happened in 2014 in TIFR balloon facilities. That time, one of our other instrument was commissioned in Hanley Telescope, SCT. And then it was followed up in 2016 at IST Trivandrum. And at that time, all of our younger active colleagues working on star formation actually made a star formation working group. And now I see large number of students and our young faculties are part of that group. And I think after this workshop, there will be more active participation and to really exchange of ideas should happen in this star forming group. And so considering this in mind, the rationale of this meeting was that since past 2 years, our two instruments were commissioned in India's largest telescope, 3.6 meter DOT. And one of the instrument is really the state of art where you can simultaneously do optical and infrared. So although we have used for scientific observations, but the idea of this workshop is that how to use it optimally. So that will be the I think we should discuss during this workshop and during the tutorials. I think that will be because it is on the India's largest telescope and it is a vast wavelength coverage. And so far it has not been optimally used. And also you have opportunities of one instrument in side port and one on main port. So I think a lot of discussion can happen in this meeting where we can familiarize PhD student, postdoc and young faculty how to use this instrument and so on. And so that is the idea. Another idea, of course, at the end of this workshop too, I think we should think about forming now working groups where we have a common science goal and so that we can optimally use our Indian facilities rather than everybody's working on the same problem and so on. So I think that's why this in-person meeting was very important. And at the beginning, we decided that we will go for in-person meeting, and thanks a lot to Director Aries that he agreed for that. We thought that online thing will not serve this purpose for this meeting, and finally we could make it. And that's why, as you see in the SOC, we have made programs such that not only we are discussing about Indian facilities and these instruments, also we are discussing a lot of interesting results which has been obtained from other facilities in abroad like ALMA and other surveys. And so one can get idea here, young student, other how to follow up those kind of work with Indian facilities and so on. So this is the rationale about this program. And finally, I thank Aries for the financial support for this meeting and also all the SOC members for their help in organizing this workshop. As Saurabh mentioned, that this auditorium was extended considering in mind this workshop, and thanks a lot to Deepankar. Actually, in a record time, in 2 months, they could make it just before this meeting, and that's why we can accommodate it in this auditorium. And once again, I thank you all of you, and I think you will have a wonderful time here and interesting scientific talks. And thank you very much. Thanks.
Yeah, thanks, Professor Oja, for briefing this conference. So now I will invite Manoj to start our first session.
Good morning, everyone. We will have our first scientific session going. So there are 2 sessions. The first session I'll share, and the post-tea session, Prasanna will be chairing. So before we start, just a quick word. And I again want to thank the organizers, Saurabh Sharma, Devendra Oja, and for organizing this, and Dipankar for his overwhelming support. Thank you, guys. And we have all been hunkering down for last 2 years, and it's good to see us. I mean, this point has been made already, but good to see all of you, in an in-person meeting. So let's start the first scientific session. There are 4 talks in this session. The first is by Sarita Vig. She will be talking about star formation and its effect on the surrounding interstellar medium. Oh, we need to get the. This. So when do you want the signal? 5 minutes. 15 minutes. So I'll just show you 5 minutes. You want to check? Yeah. Just hold it, okay.
Thank you.
All right. Time starts now.
Yeah. Good morning, everybody. So, yeah, good morning, everybody. Thank you very much. I'm very happy to be here today, and because it's my first time at Aries. For whatever reasons, my past attempts did not materialize, and I'm very happy to be here for this meeting and ASI 50 and 75 years, everything together. So today, without too much ado, I'll just start my presentation. So I'm going to talk about star formation and its effect on the interstellar media. So the plan of my talk is as follows. I'll talk about star formation and its feedback effects, and I'll give quickly 3 examples of some regions where we've been working to see some of these effects. And to begin with, this is something that everybody in star formation begins with in trying to understand. So you have a molecular cloud, and within molecular cloud, you have clumps, high density clumps, and within that, you also have higher density cores. And it is within these cores that the star formation is initiated by gravitational collapse. This is, of course, a very, very simplistic picture. So you have, after the gravitational collapse, then there is a stellar embryo at the center here. Yeah. So here you have the young protostar, and you have the material collapsing from the envelope. And because of the small amount of rotation that would have been present initially because of the collapse, this leads to the formation of a disk, and some material is also given out in the form of protostellar jets. And we believe that is responsible for the problem of the angular momentum problem that is associated with this. And as this evolves over time, you see that the molecular cloud, the core, as the envelope accretion continues, over time, you have the accretion, and it leads to the formation of pre-main sequence star. And then over time, the nuclear fusion is initiated at the center, leading to the formation of a main sequence star. In the beginning, you will have some evidence of some debris disk, and that is where the planets form. And over time, you may have the star and the planets themselves. But this is, of course, a very simplistic picture, and the paradigm has now shifted because all of us are working, and we know that things are not as simple as they appear to be. There are many other details which we are all working on, and lots of work is going on around the globe in trying to understand the various details associated with the star formation process. In particular, the formation of massive stars, the stars whose mass is greater than 8 to 10 times the mass of the sun. So these stars form on much smaller time scales, and we are trying to understand how this happens. But this formation of massive stars is also accompanied by the formation of low mass stars. So this star formation happens in clusters. So we know that it is not isolated as we have seen in the previous slide, but one has to keep the larger picture in mind where you have the molecular cloud. And what has been found is these molecular clouds are the filamentary. There are lots of filamentary structures in here. And when these filamentary structures kind of come together, there are hubs formed there, and these filamentary structures are also called ridges. And it is in these structures, the high density filaments, as well as in this, converging, the region where they converge, the hubs, is where the stars are formed, because those are the high density regions. And within that, it's not just one, but you have multiple cores being formed, and within multiple dense protostars can be formed simultaneously. And this shows the enlarged picture here. As you can see that this is, for example, if you want to see at the center what's happening, it is believed that these massive stars are formed near the very center of these clusters, and they compete for material with the surrounding regions from the surroundings accreting stars themselves. And so there is infall happening not only from the surrounding envelope, but infall happening from the cloud and the neighboring young stellar objects. And over time, a main sequence star is formed at the center, and this photoionizes the region around it. Now, even this formation of stars, people have, in order to understand this, they have tried to look at the kinematics of these regions, because there is infall of material from the filamentary structures. We are trying to see about the kinematics, at what rate the material is going into the hubs along the filament. So one of the recent studies has done this very interesting study where, using kinematics from multiple molecules, they have tried to show that they have seen that star formation can happen through these three modes. This is what they have studied in a region in torus molecular clouds. Of course, there are alternate modes as well. And what they find is that you have these filamentary clouds, and when they collide with each other, and if this happens, this collision in that mode, the star formation happens on a.
Can you use the column? See, the voice mode English is quite helpful. They have the recording thing. The students are listening to it.
So you have this fast mode of star formation which is occurring, where why do we call it fast mode? Because here the gas is moving at a faster rate. That's why it's called fast mode. And in this case, you have in the hub is where the star formation occurs. Then also star formation can happen due to the collapse of due to the collapse of the filaments itself, you can have star formation occurring, the dense core formation in the filamentary structures itself. And this is a slower mode, as they have seen that this collapse happens at a slower rate. In addition, this isolated mode has also been observed of the star formation, where a core collapses to form a dense core and a star within it. Now, let us look at this process of star formation. The star formation process that we have seen, we have just talked about how star formation occurs, but this process itself is very tempestuous, and it affects the surrounding interstellar medium in multiple ways. In the sense, as we will see, that it can affect further star formation in the cloud itself. So here is shown one particular cluster, the quintuplet cluster, and this is the quintuplet cluster. And as you can see, because of the presence of this cluster, because of the feedback associated with this cluster, you can see that the interstellar medium around it is disturbed to a large extent. Now, how does the surrounding interstellar medium get disturbed? And there are various processes by which this can happen. And the first and the foremost is the photoionization of the surrounding cloud. That is, the UV radiation from massive OB stars can ionize the surrounding medium, and leading to the formation of H2 regions. Over time, the H2 regions expand, and thus they introduce turbulence and lead to the dissipation of the molecular cloud itself. In addition, there can also be stellar winds from these massive OB stars. And these will affect the interstellar medium only if the stars are very massive, because then the stellar winds are very strong. For example, stars with mass greater than 40 solar masses, whose effective temperature is greater than 25,000 Kelvin. And the third effect is the radiation pressure, the effect of the radiation from these stars that acts on the dust grains surrounding in the interstellar medium and affects the molecular cloud itself. In addition, there are other effects like the presence of jets and outflows, which are given off from the young stars that can lead, it has been shown that even this could lead to turbulence within the cloud. Then you can have processes which are not as important, such as accretion heating. And then you can have, as the stars evolve, as we know that low mass stars and high mass stars are formed approximately at the same time, but the high mass stars evolve much faster. And consequently, when they are in the later stages of the stellar evolution, younger stars will still be evolving and would not even have reached the main sequence phase. And these massive stars could have, in the later stages, are WR stars, when they give off a lot of strong winds, and that can very strongly affect the surrounding interstellar medium. Finally, when they explode as supernovae, you can have transfer of energy and momentum. So we see that massive stars affect the interstellar medium much more than the low mass stars. And to see the effect, there are researchers who are looking at this, trying to quantize this through various simulations. And one particular case one particular example is by Grudik et al., where they have done simulations of a flattened molecular cloud, and they have included feedback effects such as supernovae, stellar winds, and radiation feedback. And they tried to see that over certain dynamical timescales, how the molecular cloud gets affected. And what they find is that over the timescales of around 2 or 3 dynamical timescales, the molecular cloud starts dispersing. And this is related to the star formation efficiency. We know that the star formation efficiency of a molecular cloud is related to is defined as what fraction of the gas is forming stars. And what they find is that initially, when the cloud is collapsing, the star formation efficiency increases, and as the stars are forming, because of the feedback effect, it reaches a maximum critical value. And beyond that, because of the dispersal, you don't have any more star formation forming, and the star formation efficiency, which is finally reached in the cloud, is a balance between gravity and the feedback effects. So the star formation efficiency, which is a very important parameter across the Milky Way as well as in other galaxies, is related heavily on these feedback effects. So if we want to observe these feedback effects observationally, how do we go about it? So there are various ways. This is difficult itself, because as we have seen just now, if you want to observe them, you need to observe them across a certain dynamical timescales, and we know we don't have that much time with us. So what we usually do is we can observe molecular clouds. You must not observe them very early on, and you must not observe them when they're very evolved. You must observe them in that intermediate phase within 1 or 2 dynamical timescales to see the effect. Secondly, you will be seeing a snapshot of the molecular cloud. From that, question is, can we try to gauge? Or you can either look at large number of molecular clouds, or you can look at one molecular cloud which is at different evolutionary stages in different parts. So I'll just talk about some examples on which we have been working on. And the first is the Rcw-42 Cloud. So this image that you see here, this is the optical image. As you can see an optical nebula here. And the photoionization that we can be probed using the H2 region from the ionized gas. So this is the radio emission from GMRT, which shows where the peak of the radio emission is. There are 2 IRAS sources here, that is regions of active star formation, and which are very bright in infrared, and that is shown in this region. This is located at a distance of approximately 6 kiloparsec. In the far infrared, before we go into feedback effects, one needs to also characterize the star formation activity here. So this is the far infrared emission here using the 100 centimeter balloon bound telescope with TFR, and you can see the 2 IRAS sources. And this central region, you can see that in the infrared, using near infrared, you can see that there is a cluster there, which means that star formation has occurred and it is at a moderately evolved stage. Let us put it that way. And what you see on the right here is the dust emission, which allows us to probe the extent of the molecular gas. So because dust is dust is a good proxy of so dust is a good proxy of the molecular gas emission. And here we are looking at the star formation activity. We have constructed the column density and temperature maps using the emission from Herschel. And the column density, the regions of high column density tells us that those are regions which are early on in terms of evolutionary phases. We have found 5 clumps in this region. What you're seeing in the center here is the dust temperature map that tells us where it is hotter and where it is relatively cooler. And what you see on the right hand side is a color composite image showing the extent of the photoionized gas. As you can see, the red color on the right hand side, that's the photoionized gas. It tends to move towards the region where there are lower density, because on the left hand side, top left, that is the northwest, you can see that there is high density region. And these are some of the characteristics of the clumps that we have found. And we have also constructed the electron density map. Now this electron density map helps us characterize the thermal feedback. And we have done this using the volume emissivity of the free thermal Brightstrahlung emission. And once we have that, using certain assumptions, we have got the electron density map. And from that, we can estimate what is the mean ionization fraction, and which is around 10% in this molecular cloud. We can also get the average thermal energy of the ionized gas and the total thermal energy. And we find that the total thermal energy is of the order of the gravitational potential energy of the clumps. Now, there are other feedback mechanisms that we can look at. For example, the energy due to the turbulence, but for that you will need molecular gas, and we are looking. We need this. What do you say? The spectral line emission from molecular gas, such as CO and so on. And right now we don't have. We are trying to look into this and trying to see if we can use that to quantize the turbulence. And this is, of course, the local star formation view of the individual sources. I will not go into too much detail here. Now, another example that I would like to give is of a supernova remnant in a molecular cloud complex. We know that massive stars evolve very fast, and therefore they would lead to the formation of a supernova, lead to supernova explosion. But we have not seen too many molecular clouds with supernova remnants. There are, in fact, very few of them that have been observed. And we can say that we were lucky enough to find a supernova remnant, which we discovered with the Giant Meter Wave Radio Telescope in a molecular cloud complex. Actually, we started off with trying to look at the star formation activity here, and then we started seeing things, strange things in using low frequency GMRT observations, non-thermal emission. And when we probed deeper, we found that there is a supernova. There is a supernova remnant, which you can see here in H alpha emission, and this is the radio emission. Here, as you can see, that the red one is the supernova emission, non-thermal emission, whereas the blue molecular, the molecular cloud through the dust emission is depicted in blue. So this was another case where we saw the effect of supernova on the molecular cloud, and as you can see, it did. You can see a lot of structures which are characteristic of turbulence. We have not quantized it, but this is something we would like to do. And finally, I would like to talk about this case about non-thermal emission from the protostellar jets. We know that protostellar jets are ejected from the young protostars in the initial phases of star formation, and initially it is the jet which is given off, but since it is within a molecular cloud, it also pushes the surrounding material in the form of an outflow. So you have the jet and the outflow acting on the surrounding interstellar medium, and the feedback effect on the molecular cloud can be in multiple ways. It can drive turbulence into the cloud, which one can characterize. What we were trying to see is the effect of the jet itself against the molecular cloud. So when the jet affects the high density molecular cloud, shocked regions are produced. These shocked regions are regions where, for example, the electrons can be accelerated to such high energies that it can give off synchrotron emission, which is what we were trying to probe. We are trying to probe using non-thermal emission. So this is one example that we were looking at. This is one of the largest protostellar jets in our galaxy, known as the HH8081 jets. And here non-thermal emission has been detected using VLA, for example, and but they could detect what they saw with VLA was a combination of thermal and non-thermal emission. What we were trying to do is trying to look at and detect only non-thermal emission. And this is one of the regions where synchrotron emission is confirmed because of polarization measurements that have been carried out. And these are very high velocity jets of the order of 500 to 1,000 kilometers per second. Now, with the GMRT again, we actually have looked at the found the detected non-thermal emission, and we were able to characterize the magnetic fields and the shocks. Our next step was to look at this in near infrared, which is an ongoing activity. In fact, yesterday and today with DOT, we were observing some of these objects with the DSL optical telescope, and we are hoping that we will get some good results there to see the shock gas in the near infrared. So there are other, I would just, that's the end. There are other couple of talks. There's a talk by Sri Lakshmi who will be talking about the modeling of these non-thermal jets, and there's a poster I encourage you to visit by Arun. And with this, I come to the end of my talk. These are the conclusions. And thank you very much for your attention.
Thanks, Harita.
Group members.
Thanks, Harita. We have time for a couple of quick questions. Yes.
Sorry.
It's self-content.
It's not self-content. It's not self-content.
Then what is it? Is synchrotron radiation still?
Yes.
Any other?
So you showed that the electron density things from the radios, it's a very largely dependent on the frequency also. So are there some comparable thing with the IR or the UV?
Yes.
I
So
don't know
with
what
the
resolution
IR,
you achieve.
yes, with IR, it is possible to do that, but we will have to take certain spectral lines in IR and take ratios of the spectral lines and do that. It is possible. We have not tried that yet, but we will be doing. Yes.
Tanspec will have some lines which can do electron density. I'm completely unaware, so just ask.
Tanspec will be near infrared. In the near infrared, the lines that you can usually probe are mostly the bracket gamma, the recombination lines mostly. Yeah, recombination lines you can get, but they will be affected by extinction. So that is an issue. You need to correct for it. Yeah, estimate the extinction.
Yeah, why I'm just asking because even in solar case, the electron density measurement from
Yes.
radio is very much frequency dependent. The value is what we get from say UV and radio.
But we in this case, this is thermal creepy, so you are actually kind of, because it's optically thin. Since it's optically thin, more or less you are,
only, so it's
Yeah.
optically thin,
So more or less, we think that it is not very far off, even though there will the variation will not be very high.
sorry,
So this is regarding the simulation result from Grudik et al. So their conclusion of that 2 to 3 dynamical time scale is where the thing.
Yes,
So
peaks, star formation efficiency peaks.
yes. So is this conclusion? So there are two parts to it. Is that been connected with any observation yet, or it is too recent?
No.
So other part was in this simulation. So what was the size and number of simulations done, and what are the possible effect of that? Is any bias coming from those
Okay,
simulation
so
into the
yeah.
control?
So they have done sizes. See, they were not trying to do molecular clouds per se. They were more interested in galactic scales. That's why they have not taken a spherical cloud or a filamentary cloud. They have actually taken a flattened, more like a cylindrical thing. And number of how many runs they have done, I have to check offhand. I cannot tell. I can check. I tell you there's another thing.
No, this was it. But this paper is published.
2018 or 19.
The picture or something.
Yes, I can give you the reference.
Let's thank Sarita once again. Thank you, Sarita. And move on to the next speaker. Lokesh, can you put this slide? next speaker is Ramesh Devangan from Physical Research Laboratory. No, but I think some of the AV students are listening to it. Yeah, that is why I had asked that to use the. But it picks up. Can you get the presentation?
So, good morning, everyone. I'm very happy to be here, and I'm very happy to see all of the staff formation community here. And before starting my presentation, I would like to thank the organizing committee for giving me opportunity to speak about my work over here. Location. There is a folder. There is a folder. Staff formation folder. There is a LKD. PDF.
Go full screen.
Yes, please. Go to the home.
So, you can see. Backward is the white book. Backward is white.
Big one is the forwarding. The small one is the backward, and top is the function.
Okay. So I'm going to talk about this one of the star forming regions where I will talk about this different filaments which face in the ionized emission, dust emission, and molecular emission. So this is one of the image of that particular region. L is equal to 345 degree, and this is a dust emission 8 micron. So these are the list of my collaborators who have been working. I've been working with them. And in this topic, I will talk about mainly the importance of massive stars, then some theories which actually explain the massive star formation, then role of filaments in the formation of massive stars, and then I will talk about the physical results related to the physical environment of this particular region which I have selected, and finally I will summarize the results. So what we know, in general, we know all the stars form in the molecular clouds. So this is a typical oh,
No, middle one.
middle is a forward. Yeah. Looking for pointing.
Pointing is the top.
Okay. So in general, we know the star formation happens in the molecular cloud. So the star formation related to the existence of molecular cloud. Then you have a dense clump, you have a core, you have a youngster object protostars, and then you have a accretion disk. So in general, we can classify these stars based on their masses. So we can say there is a low mass stars, massive stars, and intermediate mass stars. So the low mass stars and intermediate mass stars are defined less than their masses have less than 8 solar mass, and the massive stars defined their masses more than 8 solar masses. So these massive stars are very, very important in our galaxy. I will come into that. And in general, this low mass star formed through the accretion process. So thanks to the Sarita who has given a lot of information about this massive stars and other things. So I'm not going to go in more detail on that, but I would like to give some information on that. So massive stars have a significant impact on the evolution of galaxy and universe in general through their energetics. So they are the source of jets, winds, and they have a tremendous ultraviolet radiation. So you have expanding astro regions. Then they explode as a supernova, and after supernova explosion, they emit a copious amount of UV radiation, and also they enrich the surrounding through their heavy elements. And also these massive stars also are source of the shocks. So once the astro region expands, they trigger the new generation of star formation. And is the massive stars, as you say, massive star means the luminosity is very high. So these sources you can detect very far away. So these are the important things about these massive stars. So in general, if you look at the star forming ISM, our interstellar medium. So if you look at this interstellar medium in mid-infrared view, you will find so many bubbles-like structures. So these bubble-like structures are associated with the radiocontinuum emission also. So in the center, you will find the radiocontinuum emission. If you go to the longer wavelength, like sub-millimeter, let's say about 200 micron longer wavelengths of those star forming regions are your ISM, you will find filament structures. So these filament structures are very, very common in your star forming regions. So you'll have a different kind of morphologies of this filament structure in the star forming regions. So some of the filament structure you can see like elongated filament-like structure, then you have like cell-like structure, then you have a hub-like structure. So there is a central region, very dense region, and surrounded by elongated filaments. These are called the hub filament system. And in also this, so if you look at star forming region, you have a combination of this. So you will have a bubble as well as you have a filament structure in any star forming regions. So there is a role of filaments in the star formation, in particular for low mass star as well as the massive star. So one of the important thing is this hub filament system. So this kind of filaments are very common found in the star forming regions. So and the another is the end-dominated collapse. So you have elongated filaments and the star formation activity will be dominated at the edges of this kind of filamentary features. And then you have another signature or observational results related to the twisting of filaments. So you have two elongated filaments, they are twist each other. So when they twist each other, they overlap each other, so you have a high column density. So in those areas, you have star formation activity one can expect there. So these are one of the important results. And so in general, what we know about the signature of star formation? Suppose you are studying any molecular cloud. So how do you know there is a star formation activity is going or not? So if you find this kind of signature, which will allow to know there is a ongoing star formation activity, like you should get outflows, infra signature, bubbles, and ionized emissions, masers, infrared excess source rate, hard cores. So if you have this kind of signature, you can say, okay, there is a star formation activity are going on. Suppose these signatures are absent. So what you will say? So you will have a opportunity to study the pre-stellar activity in those regions or clumps. So in general, what are the difficulties we have in the massive star formation? That as you know, when you say massive means is a high luminosity. So when you have a high luminosity, you have a high radiation pressure. So suppose you apply this this accretion process, which you know for low mass star formation. So if you have a massive star, you apply this. So once the star reaches 8 solar mass or 10 solar masses, so luminosity will be very high. So radiation pressure will be very high. So it will destroy all the surrounding material. So there won't be any materials which further allow you to gain the mass for this particular source. So this is one of the fundamental problems related to the massive stars. Another is the photoionization. So this kind of sources, massive stars, they emit sufficient amount of ultraviolet radiation, so destroy the surroundings. So you have difficulties to study or infer the initial signatures of their formation. So the question is then how this massive star forms. So there are two groups of theories are available in the literature that is based on observed results. So one is this core fed scenario. So this is a turbulent core model also. Another is a clump head scenario. So what are these? And clump head scenario also consists of sub theories which related to explain the formation of massive stars. So let's see what is the core fed scenario. So in the core fed scenario, what is the most important thing? People suggested that this is a scaled up version of low mass stars. So you have a single and isolated massive pre-stellar core. As I said, pre-stellar. So you don't have signature of star formation activity. So you need a single isolated pre-stellar core for this to explain this theory. So so observationally, you should have a detection of accretion disk, and in this model, you will have a very high accretion rate. So this is the one of the important models. Now people are using this ALMA observation to get more and more candidates, but still very limited, or you say very few sources are available which follow this core fed scenario. Then you have a clump fed scenario. So in this scenario, the contrast you will get, because this scenario starts with this low stellar mass sources. So you have a low stellar mass clump core. So it gets material from the larger scale and then it gains the mass. So this is a very popular theory nowadays. And one of the most example I'm going to show that. So here there is a cartoon shows that you have a big molecular cloud, then you have a filamentary structure, clumps and core. So material inflow from the larger scale to the smaller scale. So this is the one of the most important scenario. So it's related to this scenario. This is the most common thing is hub filament system. So as already I told you some about this, some information about this. So you have a central core here, central region, and this central region, this is called hub, and this is surrounded by filaments. So what is the filament? In general, you have a long elongated feature. So how do you define filament? So you have a length and you have a width of the filament. So you take a ratio of that. So that is called aspect ratio. So this filamentary ratio, features have a high aspect ratio. So you can easily identify these filamentary features. So this is the and also central region has a higher density, higher column density compared to the filamentary features. So this is the one of the theories or model which explain the formation of massive stars. So people say that, as I said in one of the model, that there is a core fed scenario. There is an existence of a single isolated pre-stellar massive core. But in this model, they suggest that there is no existence of very high mass pre-stellar core. So everything starts with the low mass, and then with the evolution, they become gain the mass from their surrounding, and they become a massive star. They form massive star, and then they start ionizing, and that you form asteroism. So this is the scenario of this. And another popular theory is a cloud-cloud collision. So you have two clouds, they are high relative velocity, and they collide each other. Once they collide each other, so there is a small cloud and there is a big cloud. They collide each other. So they form the compressed layer. So this is a shock compressed layer. You have where you expect very high column density. So you form a dense clump. So this is the location where you can form the massive stars. So this model also explains how the massive star forms. And also there is an application of this cloud-cloud collision is you can also explain the existence of hub filament system by this model. So what they say, when the collision happened, so you have a shock compressed layer. So within the shock compressed layer, they form which fragment, the shock compressed layer fragments into the filaments. And these filaments form a network or like spiral-like webs. So the hub filament system can be formed through this cloud-cloud collision. So this is one of the very latest work on this cloud-cloud collision related to this G31.1 hub filament system. And they have reported the signature of cloud-cloud collision, which explain the existence of this hub central hub. So this filamentary feature, they collide and they form a central hub. So this is one of the results related to this cloud-cloud collision. So far we have been talking about dust filament, molecular filaments. What about ionized filaments? So do we have any ionized filament in our star forming regions, or really they do exist or they don't exist? So in this scenario or in this aspect, I found in literature there is a one star forming regions is a LBL. So in this region, you are looking at the image is 1.4 gigahertz. So this is, you see the violet structure. So this is ionized emission. So this you can consider as ionized filamentary features. So also now what people are looking for, they try to understand the connection of this cloud-cloud collision and the hub filament system. So this aspect is observationally is limited so far. So people are working on that. So in this, considering this aspect, I have been working, I have selected one star forming region around this L45, this region. So I'm going to show you some of the results related to this. So these are the data sets I have been using. So this is a multivalent data set I have been using. So I'm starting from near infrared, mid infrared, far infrared, sub-millimeter, millimeter to radio centimeter. So which traces your ionized gas, dust filament, molecular gas, wire source. So you can trace all the components associated with the star forming regions. So this is a 8 micron image of that L45 region. So you can see nicely there is a bubble-like structure. This bubble-like structure is there, and there is a filament elongated like features are there, and also you see the dark filamentary features are there. So these are absorption features, and these are the emission features. So if you look at the same field of view in the sub-millimeter allows to trace the very cold dust and clumps of that region. So you can see. And also I have overlaid these clumps, which are marked by these stars and these filled circles. So you can also, you have the information on distances of these clumps. So field star, they are located at 2.4 kiloparsec, and this field circles, they are located at 1.4 kiloparsec. So when you select the large field of view, so there is a problem. The problem is, are you dealing with a physical system, or they are like this along the line of sight? There is a problem. So some system may be like this, may not like, maybe like this. So we don't know. So we should have information of distances to know, confirm that we are really dealing with a physical system or not. So you can nicely see there is a star like this, star symbols that present one star forming region, and this you see there is a elongated structure here. So this is the radio continuum image at 843 megahertz. So this is a you can trace the ionized emission. As I said earlier, when you look at any filaments, so what we look for? We look for the aspect ratio. So if you say that any feature is elongated or not, so you immediately look for the aspect ratio and you say, okay, this is a filament structure. So here you can see there is some filament structure can be considered here, and also there is elongated. This is all ionized emission. So this is radio continuum emission I'm talking about. So we can consider that is maybe is an ionized filaments. So if you look at the same field of view in molecular emission, you can see there is a box here. So I'm zooming this box region only, not the entire field of view. So if you look at this box region using this,
look at 3 more minutes.
Yeah, just so you have a RGB map, and you have a filament structure here, and you have then you can look at the molecular cloud, the molecular gas distribution along the same field of view. So you can see you also have overlaid this dust continuum positions over there, and so here I am just presenting the distribution of molecular gas and ionized emission, and here there is I have identified all the protostars again the molecular emission. So this is again, this is a MOPRA data. This is 90 arc seconds, is a molecular. Now I am using high resolution, which has this 42 arc seconds. So you can nicely trace this. I study the morphology and structure. You can always distinguish the structure because of high resolution data. So what we see here, so I have made this RG map, 2-color composite, and I find there is the molecular emission and ionized emission here. There is a one filament structure, and there is this one I'm talking about. This is one ionized filament A, and there is another ionized filament. This is IB, and you can see the parent cloud associated with this. So here we found there is a signature of 2 clouds here, which are marked here. So here we have also studied the position. Well, this is a temperature map, so you can dust temperature map. So you can see the warm dust emission associated with these S2 regions. And we have also studied the position velocity diagram along these different curves and arrows. So, to analyzing this, we found that there are signature of 2 velocity components. So here you can see this is a PB. This is a PB and this is a AA. So along this we have extracted that this is a AA and this is a PB. So here we found the signature of 2 velocity components. So also you can extract the position velocity diagram along this curve PP, QR, and QS. So you'll find there is a signature of outflows, and also there is signature of 2 velocity components.
Finish 1 more minute.
Yeah, just so we found there is a 2 velocity component in this region, and this is a zoomed in view of this one of the top IF is associated with that. So here you can see high resolution near infrared images, and further this is a massive protostar. You can see the inner environment of the source, and this is the different molecular maps of moment 0, moment 1 of the associated with that. And also we have studied the position velocity diagram and found there is a 2 velocity components. And when you study the distribution of these 2 velocity components, you'll find this all the massive stars and the protostars, they are seen at the overlapping zones of these 2 clouds. So we find there is a signature of cloud-cloud collision here, and also this cloud-cloud collision may explain the Hawk filament system. And also what if time, I think time doesn't permit, but there is also possibility you can study the impact of O star which form in the filament, or this O star impact the filament. So this O star can destroy the filaments, or this filaments can sustain against this ionizing feedback of the O star. So the important points are take home message from my talk is shown here.
Okay, yeah. Thank you, Nagesh. We can take a couple of quick questions. Yeah, Sarita. And then Tapas. Yeah.
So, I just wanted to inquire about these ionized filaments. So, filaments could be higher density regions. So, when ionization happens due to the stars, the photoionization, you would expect that it would move towards the expansion would happen towards lower densities compared to higher densities. So, what is actually ionizing the entire filamент?
Yeah, that is the common scenario. We know that when you have a massive star, then it expands and the ionized region expands. But in this case, elongated filaments, sometimes it happens there is a nearby very massive stars. So from those nearby massive stars, these ultraviolet photons may leak, and that may allow
external ionization.
But also there is a possibility once this elongated filamentary features are formed, they are always associated with the ionized emission. So when the massive star also formed there, so locally this massive star starts ionizing. So this you can say combined feedback may also explain the existence of the ionized filament. So only one or two sources are known in the literature.
Tapas?
Actually, that question is asked already.
Yeah, listen quickly. Yeah.
You mentioned about calculating the aspect ratio, right? I mean, of the filament.
So simply what we saw, we have a length and width.
Yeah,
so
yeah.
You take a ratio.
So how will you account for the projection effects? Because the filament can along, let's say, that direction. But when you are seeing
So
it in
when you have a molecular line data, I think it's possible to do that. I will. You can do that. You can ensure that.
Okay, thanks, Lokesh. Let's thank Lokesh for his talk and move on to the next speaker, who is Jesse. Yeah. Can you please get your presentation? Jesse, use the column.
It's in the desktop.
Student room का नहीं वहाँ का स्टूडेंट रूम.
You got the presentation?
Folder में जाना. Yes, the top one is the pointer, big one is for going forward, and the bottom one is for going backwards.
Full screen, I'll go to the right. So, Jesse, 17 minutes.
Okay.
So I'll give you 3 minutes, one after 14 minutes. Okay.
Sure.
Oh. Okay.
Just follow me.
Yes.
Just switch on. Just shift it. Shift it.
This side. Fine. Good morning, all of you. First of all, very happy to be here, and thanks to the organizers for organizing this wonderful talk. So most of you may not know me, so I did my PhD from this place years ago. So I'm very happy to be back here and giving this talk. So I'll be talking about star formation in diverse environments. Both the speakers before me talked about various feedback, environment effect, etc. So I'll be talking about the regions in different distances in the Milky Way. So starting from solar neighborhood to the extreme outer end of the galaxy. So I'm talking on behalf of the student and postdoc team at ISO Tirupati. So few PhD students and postdoc and master's thesis students and the outside collaborators. It's not changing.
Now it will go.
Okay. Yeah. IMF, initial mass function, as we all know, this is one of the fundamental outcome of star-forming event. It is the distribution of stellar mass, like a stellar mass versus number. If you plot, that's IMF, and it has a big implication in the context of star formation. It imposes a large constraint on star formation process, and it is very important in order to understand several aspects. For example, in order to understand our own solar system kind of star forming event, or any galaxy formation, Milky Way star forming regions, galaxy evolution, dynamical evolution, as well as in order to understand the chemical and dynamical evolution of the galaxy and the cosmic evolution as such. In order to understand this, initial mass function is a fundamental parameter which we all should know. So what is the typical form of IMF? There have been several forms which are claimed in the past. So the right side plot shows the mass versus number of stars, and obviously it has several forms. So the well-known salpeter slope or salpeter form of IMF, which is this blue line, which has a power law slope with the slope around 1.35. And then other forms like Miller scale, Okerova, 2001 model, Chabrier, it has evolved into many different forms in several studies in the past. What I want to highlight here, the form of IMF in the high mass end and the low mass end. So if you look at this, the high mass end, above 1 solar mass, it's largely generally agrees with the salpeter slope. But the low mass end, there are a lot of discrepancies. There's discrepancies in the form predicted by different researchers as well as in various observation and analysis. So the low mass end is more important in a given galaxy or a given star forming event, because the total stellar mass of galaxy or a cluster is defined by mostly governed by the low mass end of IMF. So this part of the IMF need to be well constrained. And there are a lot of claims for non-uniform IMF in extreme environments, such as galactic center, as we all know. The environment of galactic center in terms of the radiation strength or dynamical influence, the galactic center is very different than compared to any other solar neighborhood or other regions. And also, the Milky Way satellite galaxies, apical galaxies. So there have been already studies addressing this issue, whether the IMF is uniform or not. So the important question, the unsolved questions in the field of IMF is to what extent we can assume the universality of IMF, even if we can assume it up to what extent, and whether the environment play any major role in shaping the form of IMF. So I'll be addressing few environmental aspects here. For example, radiation feedback, which already the speakers before me, they already talked about the various feedback effect on star formation contest. And so other than that, I'll be addressing the stellar density, because when you have different dense population in a cluster or a galaxy, your dynamical effect will be different. So as such, how the IMF can vary, then metallicity and galactocentric distance. So these are the various aspects I'm going to address here. Yeah. So once you move from solar neighborhood to the distant galaxy, distant part of the galaxy or our own galaxy, the environment is completely different. And the studies also, we cannot use the same technique to address the same IMF initial mass function when we move from solar neighborhood to distant regions such as 8 kiloparsec or 10 kiloparsec. So I'll be addressing some of the techniques which we implement here. So where are we standing in the context of IMF? Where are we standing right now? So those regions within 500 parsec, they're all well covered spectroscopically down to at least brown dwarf regime. That means 0.08 solar mass within 500. So that I don't need to look at it. But how about the brown dwarf regime? Brown dwarfs are, we know, they are low mass objects. They cannot burn hydrogen in the future, and they are like a low mass object. It starts from 0.08 solar mass to few Jupiter mass. That's a mass range. So even in the like a solar neighborhood, this is 500 parsec the so-called solar neighborhood, the brown dwarfs are not well constrained, or it's a form of IMF is not well constrained. And within 2 kiloparsec distance, so we all know that it's roughly solar metallicity. So we cannot implement the same spectroscopic analysis there because things are different. So these regions are crowded. Spectroscopy is not possible. So we have to largely rely on photometric technique. And our current survey or any of the observational technique which can largely cover down to brown dwarf. But outer galaxy, when I talk about outer galaxy, this anti-center direction up to 16 in terms of galactocentric distance up to 1670. These are the regions beyond our limit. Still, it's doable. But they're the things that I would like to highlight that the outer galaxy environment are completely different. So most of you know that in terms of low metallicity, these regions are well known for its low metallicity, low atomic to gas, molecular gas fraction, low staff formation rate, low radiation strength when compared to solar neighborhood. So the staff formation, also the mass surface density, the gas mass surface density is completely low when compared to the nearby regions in the solar neighborhood. So one has to address how the environment or these environmental aspects are affecting the form of IMF. But it's equally challenging because as we move to the outer galaxy, the spatial crowding, we need high sensitive observations in order to address the extreme distant galactic regions. So so the conclusion is we cannot have the same approach to obtain the IMF of nearby regions and the distant regions. So we implement 3 different methods here. One is for the nearby regions within 500 parsec. We employ the water band based imaging technique to identify the brown dwarfs because brown dwarfs is the one we are lacking as of now. So we use as a special technique. And then for those regions within 2 kpc within the solar metallicity environment, we use the multi-band SCDA analysis. And the outer galaxy, of course, we have to rely on the statistical analysis. So coming to the nearby world within 500 parsec, we have been involved in a survey of nearby star forming regions using the water band imager, which is a W band filter at a 1.4 micron. It comes between J and H. It's a very narrow band filter. And the speciality of this, we all know that the brown dwarfs have huge water content in their atmosphere. So the radiation from the brown dwarfs, the host brown dwarf self-absorb due to the presence of the water atmosphere. And then what you get is an observed huge absorption at about 1.4. So when we observe, suppose a G2 main sequence star compared to the brown dwarf have very huge absorption, and then the W band it is like a very faint when compared to J and H band. So we can use this spectral index using J, H, and W band combination. We can use this is a very effective way to screen the brown dwarfs with water content in their atmosphere. So this is a very efficient method, and we have been involved in a survey of nearby star forming region within 500, several of them nearly 10 star forming regions. So this is in a crowded regions like this, J versus J minus H. This pointer is also, I think the battery is weak.
It's okay.
So I'm not getting.
Just
Yeah. So in a region like Serpents, which is one of the very young active star forming region, and J versus J minus H, you can see how the photometry method is efficiently identifying the brown dwarfs. But that is a form of photometry technique. Once you have the screen sources, photometry screen sources, you need spectroscopic confirmation. So we use all kind of spectral data from various telescopes like Gemini. We have taken DOT, transfer data as well, CTIO, Paloma. These are some of the observations which we took for spectroscopic confirmation. And right side is the result of one of the results of our star forming region, which is sigma Ori. So the details of this technical details will be given by my student Belinda later. After 2 days, she is giving a talk. So I would like to say that we constrain the form of IMF to extreme low mass, and this is about 3 Jupiter mass, and this is the first time we are going deep in the form of IMF, such a low mass. So it shows that the power law form is more favorable for this region compared to the log mass, log normal form of IMF. So more details will be given in her talk. And beyond solar neighborhood, so within 500 parsecs, we can rely on this W1 imaging technique, but beyond 500, that's a limit, current limit with the existing technique and observing facilities. So beyond solar neighborhood, we use the multi-band SCD analysis for identifying the membership of star forming regions. So we use deep optical observations using Subaru and hypersuperintended, it's a wide field in optical imager in Subaru, and CFSD UFIS, these are the near infrared data which we take. So we have, once we have the SCD analysis, we can effectively identify the membership of a given star forming region. So this is such an example, parameter diagram R versus R minus Y. We're using this is the Subaru data, so which we essentially go down to 26, 27 magnitude. So all these highlighted sources towards the right end is the SCD based pre-main sequence source identified in a region which is at a distance about 2 kiloparsec. So this talk also will be given by one of my students later. So what about the beyond 2 kpc, the extreme outer end of the galaxy? So the conditions are completely different, as I mentioned. So we have been involved in a survey of star forming regions in the outer galaxy. The radial distances between 10 to 17 kiloparsec using deep NIR analysis, CFSD and UKIS based 4 meter class based telescope, deep NIR analysis. So these are the spatial distribution of the star forming regions. So all these white circles are the solar metallicity regions and the star marks are the low metallicity region. There will be another talk by Sudeshna addressing the dense gas population or dense gas distribution of these regions. So on the right side, what we show is the galactocentric distance versus the metallicity log O by H for this region. So this is the solar metallicity, and you can see that the subsolar metallicity regions are relatively low in terms of the metallicity. So we pick such regions we have they have relatively low solar metallicity compared to Sun. So once we have the deeper NIR data for the distant regions, we have to rely on statistical analysis to identify the membership and the physical parameters. So this is the technique which we use. Basically, we field decontamination. We use a statistical subtraction technique to obtain the possible pre-main sequence branch. Then we obtain the extinction and age estimation using the HR diagram analysis, and then mass magnitude relation, and finally we get the mass of individual star and then the form of IMF. So here is the IMF distribution of 23 star forming regions, both solar metallicity and subsolar metallicity. So on the left side, this is complete. This is IMF distribution for solar metallicity. Yeah, sure. This is for the subsolar metallicity. So this is the first deepest survey on IMF down to 0.1 solar mass. So our survey is complete down to 0.1 solar mass. So this is an average form of IMF for both the regions, both the set of regions. One is for the solar metallicity, the other one is for low metallicity. So the characteristic mass, this is the peak mass in the IMF distribution, so MC, and the spread in the distribution. So MC is 0.31 here it is 0.38. So our survey shows that irrespective of the metallicity, both have the almost same characteristic peak mass and the sigma. And here is the distribution of, we also verified or checked the distribution of MC characteristic peak IMF mass as a function of UV radiation strength. So if you look at the x-axis, our UV radiation strength in those individual regions, it has a huge range between 2.5 to 6.5 in log scale. So it's of the order of 4. And the characteristic mass remains almost same. This is for a nearby region, and this is for the solar metallicity region. And this is in terms of stellar density, because we want to check whether the IMF, the characteristic mass, especially whether it has any role based on its peak stellar density. So this is the distribution. Here is the distribution of spatial distribution in terms of RG for the solar metallicity on the left side, and this is for the subsolar metallicity. So subsolar metallicity, you have a huge spread in the MC value, but within uncertainty of individual regions, you can say that the MC is comparable to the solar metallicity regions. And this is metallicity as a function of MC, the characteristic mass. So very extreme low metallicity. These are the extremely distant regions in our survey. So it goes like a slightly, you have an increasing trend as a function of metallicity, but it's like a individual uncertainty if you consider it's all within uncertainty limit. On the right side is a theoretical estimation of IMF by Matthew and Ferrer in 2021. So this histogram shows the distribution of IMF after taking care of all effect or kind of several feedback components such as gravity, turbulence, magnetic field, and radiation and outflow. And this red curve is our own IMF, which is published in Damian 2021. So the theoretical work after implementing all the feedback and our work after considering all this environmental effect, so they are very well correlated when compared to other models. So this is one thing which I would like to compare. So we are also involved in the circumstellar disk properties as a function of metallicity. So we use the H alpha based and UV based excess emission of pre-main sequence source and convert them into accretion luminosity and mass accretion rate, and eventually we like to see the role of metallicity on these parameters. So here I would like to summarize the work. So we have been involved in a large observational survey of star-forming regions evolving under diverse conditions and starting from solar neighborhood to the distant galaxy. So we like to address the question of the role of stellar density, radiation strength, galactic location, and metallicity on the form of IMF and circumstellar disk properties. So this is the first deepest survey on this study especially for the outer galaxy. And so yeah, our studies shows that there is no systematic variation of IMF, although it shows widespread in the characteristic mass for the low metallicity and distant star-forming regions. So ongoing work includes the circumstellar disk properties using H alpha and UV based photometry based analysis of these regions. And we definitely would like to go beyond this region. So yeah. So we are planning some deeper observations, and our proposals, including the JWST, is accepted for the next cycle.
Thank you, Jesse. Thank you for this fascinating talk. We'd like to questions. Salman, Dasan, and after that, Salman.
Okay, Jesse, nice talk. So actually, I am curious to know about your water and imaging in the detecting downward. Because you face lots of contamination with the rate M2. That is because once you go to the input to groundwork, water content actually reduced. Then we are much rely on the methane bank. Of course, methane for very late groundwork. Okay. So in this region, how you differentiate the rate in works, the before background?
Right.
What will be
So, the main thing in this background brown dwarfs will be very faint.
No, background M dwarf.
Background M dwarfs, right?
Yeah.
Okay. So that is so you have the water content. So for M6 and later, like M6, M7, the brown dwarf, they have more water content compared to M3, M2, M1. So this index value, the slope will be less for the early M type when compared to late M type. So that is one reason. So we can, using this Q index, we have a specific cutoff for M6 and lower value. And using this cutoff, we can screen the background early type M stars. So I do agree there are water content for early M types also, but not as deep as this one.
Listen. Someone, sorry, we have too many.
Just 1 second. Then do you have a calibration part in the new groundwork to the water?
Yes, so we have 90% confirmation on this. So with the known regions, we repeated these observations and we have 90% confirmation.
Listen.
A quick question: how do you estimate the metallicity of this region?
Okay, so that is literature-based metallicity, and they measured the nebular line-based metallicity, not the stellar-based abundance. It's a nebular-based metallicity measurement. It's from the literature.
Brijesh?
Yeah, I think partly. So when
ask a similar thing. Completeness factor, how do you address that those
Right.
labels, because you are touching a very nuance.
Right. So we have these regions are especially low extinction. So we handpicked some regions which are very low extinction. And that was the main challenge. So that our deeper observation, this is CFST based unified observation. So they largely, because we have deeper observations, it's down to 0.1.
Last question from Sarma.
Yeah, well, Vijesh has already asked part of my question, but other layman's question, I'm not familiar with this. So this W band imaging, how is it done? Means I'm curious because it is between, it's not, I mean, ground based, how do you do this?
It's a CFST widecam imager. It has W band installed. So it's a customized
Atmospheric absorption.
right. So that's why we need Hawaii and site. So far it's only in Hawaii and HST. These are the only two facilities which has W band. So definitely water absorption around telluric lines will be distorted, but this is much lower than that. This absorption is much deeper than our own water content in the atmosphere. But we need extreme dry side. So if it is humid, more humid and this observation is not recommended.
Yeah. News to me, because I thought all the bands were defined based on where it is difficult to do, but you are saying you can beat it at 4 kilometers height from the sea level?
Right. Yes, sir.
Techniques are slightly different. Maybe I'm not understanding. Maybe we can discuss offline.
Oh, okay.
There is anyway very nice talk.
Online question. Oh, there is. Yeah, I think we should take one here. Can you please online question? Can you allow? Yeah. Anapuni, can you hear us? Please go ahead if you have a question.
Yeah, I have a question. You can hear me, I guess.
Yes.
Yeah. So this is regarding the completeness of the data. So how do you make sure that the data is complete at the bright end as well as in the faint end in the data? Because you're counting numbers for the IMF.
Right. So we have two methods. One is the artificial star method to obtain the IM all of the completeness, as well as we use the histogram method to obtain the completeness. So for most of the regions, so like a 90% completeness down to certain magnitude limit or mass limit, that's what we consider. So the the artificial star method we have implemented for completeness mission. So as I mentioned, these are handpicked regions which have relatively low extinction. So if you go to high extinction, the completeness is low or poor. So we handpick regions which have relatively low extinction.
Yeah. Okay. Yeah. Thanks.
Okay. Let's thank Jessie again for that very interesting and fascinating talk. Thank you, Jessie. Our next speaker is Sudeshna Patra. She will continue with the overview that Jessie has given us. She will talk about the star formation in outer versus inner Milky Way. You're switch on?
Yeah.
So no.
No, just fix it up. Fix it on.
So this one is for coming. Okay, this is for going forward. The big one is for going forward.
Go back.
Good morning, everyone. First of all, I would like to thank the organizer for making this meeting in person and giving us a chance to meet everyone. So today I'll be talking about a comparative analysis between outer and inner Milky Way. So I'd like to introduce my collaborators briefly. Professor Neil Evans from University of Texas at Austin. JC, she's my supervisor in Tirupati. Akite Kim, he's from Kasi, South Korea. Mark Heyer, he's from UMass Amherst. Jens, he's from MIT. Manas Samal, he's from PRM. And Swagat is a postdoc in Amherst. So the pioneering studies by Gayo and Solomon they have shown that there is a strong linear relation between the HCN luminosity, the lowest transition like 1 to 0, and the FIR luminosity, which is basically an indicator of stuff formation rate for the whole galaxies. So there is a tight linear correlation. So this plot, it shows the linear correlation. So the bottom, that unfilled circles, these are like for normal spiral galaxies, and the upper filled circles, these are for luminous and ultra luminous infrared galaxies. So, and when Wu et al. Later on extend these studies for galactic clouds, they showed that same relation. But now the question is, do the dense gas tracer probe only the dense gas? So the several studies recently, they showed that a substantial fraction of luminosity are coming outside the dense part, like from the diffuse part. So here in this plot, this right vertical line, it shows the dense plumb position. Okay, so this is an integrated intensity plot of HCO plus and HCN with from the peak position. It's like if you are going far. Okay, so now this outside this region, like black shaded region. So these are like showing that positive and negative as you are going far from the dense part, denser part. So now if you just smooth it, and this green line shows the smooth line, so you will see this as a positive bias there. So that means it's a significant amount of luminosity coming from the lace, like from the diffuse part. So for this particular target, this is like 72% luminosity coming from outside the dense region. So this kind of studies have been done for RNB, RNA, and inner galaxy clouds. So outer galaxy regions are unexplored. So this is a motivation for us to take up outer galaxy regions for our study. So before going to the outer galaxy results, so I'll give a brief like why it is happening. So the critical density, which is defined by the like balance between spontaneous radiative decay and the collisional de-excitation. So that for millimeter wavelength lies near the thermalization, that point NC. Okay, so but most of the millimeter emission is coming well below that critical density, like subthermal emission. So and also if you in reality, if you drop the two-level approximation model, then you have to incorporate that high transitions and also radiative trapping. So if you incorporate all those things, then it will lower down your effective excitation density, which is defined as the density needed to detect a molecular line with integrated intensity of 1 Kelvin per kilometer second. So typically for the lowest transition, like 1 to 0, this factor, like which is lowering, it's like order of 1 to 2 magnitude from the critical densities. So for HC and HCO plus, it's like 4.5 into 10 to the power 3 and 5.3 into 10 to the power 2 per centimeter cube, whereas their critical densities of the order of 10 to the power 5 and 10 to the power 4. So this discrepancy has been seen like significant in the lowest transition. So in the previous talk, JCC already introduced like how outer galaxy environments are very different from the galactic center and like from the inner part. So that's like a motivation for us, like to study. So by studying these regions, we can like bridge the galactic studies and extragalactic studies, like mainly those dwarf galaxies. Now we have like total 19 samples, this white and red points with a barocentric distance from 9.85 to 17 kiloparsec, whose heliocentric distance corresponds to like 2 to 9 kiloparsec. And this is a combination of solar and subsolar regions with the metallicity oxygen abundance. Basically, it's given from 8.02 to 8.59. And this yellow points, 6 points, those are inner galaxy clouds studied by Evans. So finally, we will be like comparing with those clouds. And particularly in this talk, I'm presenting this 7 regions, 12 regions we yet to work on. So all this observation has been taken from single-dish radio telescope in Kasi. So it's a 14-meter telescope, and it's working in frequency range of 85 to 115 gigahertz. So we have looked at their HCN and HCO plus observation, and also we have looked at other lines like their 13C part also. So other data which I have used is 12CO, 13CO. Those are taken from FCRO, and thermal dust continuum emission from BGPS. So the mapping area, mostly we have taken like 50 by 34 arc minute. Like this is an one example case for SH2254. So we need a really large area, like large area to map like the diffuse part also, because finally we want to see like how much emission coming from the diffuse part. So the main traces, dense gas traces are extinction threshold, then 1.1 millimeter continuum emission, and dense line traces HC and HCO plus mainly. So we define the dense region as E. So we have studied in 2 ways. Like one is extinction based analysis, another is BGPS based analysis. So in extinction based analysis, we have taken H magnitude as the limiting. Like beyond that, we will call them as in region. And BGPS, we have BGPS mask available in the website. So you can take that and consider them as BGPS plum. And for total region, anything above like AB greater than 0 magnitude, we are calling them as total region. So now we'll coming to the result part. So we calculated fractional luminosity. So that is basically the luminosity coming from the in region divided by the luminosity coming from the total. So in this plot, you can see this fractional luminosity versus the clouds. So it's ranging from 0 to 0.6. So significant amount of luminosity are coming from the outside, like from the diffuse part for most of the clouds. And this is a similar result with the inner galaxy clouds, what Evans et al. Had seen before. So now coming to the another interesting result. So that is related with the mass conversion factor. So it's defined as the ratio between mass by the luminosity, and this parameter is extensively used in extragalactic studies where you can measure the mass directly from the luminosity by multiplying this factor. So Gaia and Solomon first, like they measured this for the normal galaxies. So it's like they got it's like 10. And when Wu et al. They had done this studies for galactic dense clouds, so it is like 20. So there is a discrepancy between this number. It's like 2 times of that. So why this discrepancy is coming? So when we are looking at the extragalactic studies, basically that is unresolved observation. So this picture, this galaxy pictures, this is NGC 5194 from Empire study by Gemini's Donario. They had observed it with Iron 30 telescope. So, so the resolution is of the order of 1 to 2 kiloparsec. So this white contours is like HCN 120 lines. So whereas in the right side plot, it's the galactic plum for SH255 has been studied by Wu et al. So where they have mapped only the dense part, they didn't even map the whole region, and that map size of the order 15%. So it's which is much lesser than the like your galaxy like whole galaxy scale. So that means when we are looking at extragalactic part, so that is we are looking at dense plus diffuse region, and that's why this discrepancy is coming. So we want to look at that.
So there's not 2 minutes.
Oh, okay. So we have measured the dense gas mass from that BGPS data, and you can convert that into the alpha factor by dividing the total luminosity and like dividing the luminosity only from the in region. So that will be called as alpha total and alpha in. So now the value what we got for the outer galaxy, we have got alpha in is 19. Inner galaxy it was like 20. And if you just see that galactic dense limit is like 20. So it's, if you are only looking the dense part, then it's consistent with the galactic studies. And if you are considering the whole region, then it is consistent with the extragalactic studies. And this is a corresponding plot which I made for with RG, how it is varied. So this is a conclusion from this part of the result. Now, another important hint we got, interesting hint basically, the potential impact of metallicity. So we have used HCN and HCO plus, both are linear molecule, but N and O, like the chemical difference is there. So with that, we can expect that it can relate with the chemistry of interstellar media. So if you take the total luminosities ratio of HCO plus by HCN, so outer galaxy it is like inner galaxy it is 0.56, so rate points with the and mean is shown with the dotted, dashed lines. And outer galaxy it is 1.12, those blue points. And this is like higher. Now that part is consistent with the studies have been shown by low metallicity extragalactic system like LM-CSMC, which is like dwarf, and they had to get a range of 1.1 to 3. So the shaded region shows that range. So it's like we can say that HCO plus is more luminous than HCN in the low metallicity environment. So currently I am working on mainly 2 parts, another 2 parts. Basically, one is, yeah, it's done. So NIR study, basically, where final aim is to get the star formation rate efficiency. For that, we need stellar mass, age, and cloud mass. For stellar mass, for the NIR data we need, so that we are taking from UKIDS, and we have submitted proposal for deeper data in LBT and CFST. And molecular line study, we will extend this work for another 12 regions, and we will explore the metallicity aspect in detail. So these are the main 3 conclusions which I discussed today. Thank you.
Thank you, Sudeshna. We'll take questions now. So Lokesh first, Swarna, and then Tapas.
Hello. So why we are using SCO? We can go for S13CO plus, right? Because you need to trace the densest gas. So S13CO plus is better than SCO plus. It is HCO plus. You are using SCO plus, right?
Yeah.
So I'm asking why you are not using S13CO.
Yeah, we have looked at H13CO also, but like we want to compare with the inner galaxy studies where HCN and HCO plus is used, and mostly in the extragalactic studies, HCN, HCO plus are like more used tracer. So we compared HCN, HCO plus.
But you mentioned that when you use the SCN, there is a diffuse and dense, there is a both, right, in the extragalactic case. Suppose you go for S13CO plus.
Obviously, that will probe the more denser part. Yeah, that will be.
Another thing that you use the AB is equal to 8.
Yes.
So what is the corresponding column density value for?
It will be like 10 to the power 20, like 1 into 10 to the power 21, like 18 to 10 to the power 21.
So you say that is the densest region.
No, this is like we define that because most of the YSOs you can find above that column density. So this Lada and Heidemann, they had studied already. So above 8 magnitude, you can find most of the YSOs. So we are calling that anything above
that
8.
Maybe that depend on the direction, which direction.
Lokesh, I think we should take it offline. Yes, sir. Next question.
So this is related to your comment on critical density, effective critical density, and effective, which you said is changing by 1 to 2 decks primarily because of the simple model of 2 level versus the detailed model. So does such effect will work for diatomic molecule also, for like CO, for example, or?
So yeah, it affects mostly it affects on HC and HCO plus. But the difference is more in HC and HCO plus. If you see, like
I'm curious for CO, what would be the effect? Like nothing, no effect, or?
Yeah, CO also there is effect. Yeah, so there is.
So is it because of di versus tri or something else? Means what is the underlying reason, the level diagram? Because one is talking of radiative, the competition between collisional and radioactive excitation. Right? So what is the, because 1 to 2 decks seems very big effect. There has to be a reason. So maybe we can.
Tapas.
showed that HCO plus by HCN, that ratio 0.5 and 1.1
Yeah.
towards inner and outer galaxy. So what causes that? Is it because the ionizing radiation is lesser towards the outer galaxy, or what is the reason for
It
such?
might be because HCO plus is sensitive because it's iron, and we are thinking that it might be because of the metallicity also it can affect. So that part we yet to explore. So for that we planning for, like, we have observing a higher transition. So that observation we are taking from ethics to look at that one, because HCO plus has critical density or effective density less than HCN. So we can say that, okay, because of that also it's happening. So we are not sure. So we have looking for the higher transition also.
Okay. Thanks everyone. Thanks Sudeshna for a very interesting talk, a very intriguing result. We'll have to end the session now. We're praying for tea now. So before you go, Saurav wants me to announce that there is a photo session happening during this break. So please be available. And we will reconvene at 12. So as you can see, as per the schedule, it is 11:45. We are running behind. So we will reconvene at 12. Sharp. Thank you. Yeah.
Next set of speakers.
The speakers for the next session, please upload your talks on the PC.
Where is?
Sorry, sir.
এটা পিডিএফ ফাইল না কোথায় কপি করতে ওইটা जावेद जी पॉइंटर है ना वो इधर दिखाएंगे तो उधर उसका हाथ दिखा रहा है एक बार
speakers in this session. And I request the speakers to stick on to time. So the first speaker is my friend Thabas, and he will be talking about protostellar outflows and their orientation with false filaments in massive protoclusters. Thabas, 15 plus 5.
Sure, 1 minute.
Yeah, okay.
Okay. So first of all, I would like to thank the organizers, Aries and TFR, for organizing this event in person. Because after a long time, we get to see each other. And a lot of star formation people here. So today, I'm going to talk about a little bit about protostellar outflows and their orientation, relation with their host filaments. So this is the brief outline of my talk. So first, I will introduce what are the filaments, what are their importance, and why should I look for the orientation between outflows and filaments, and few of our studies, and then I will summarize that. And finally, I will present a couple of slides on the prospect of using such studies, prospect of TANSPEC for such kind of studies. So as I mentioned, so what are the filaments? Filaments, to different people bring it different things in their mind. For example, muscle also contains filament. Tungsten bulb also contains filament. 3D printer also has filamentary structures. And solar physicist, the director is not here. So solar physicist will understand the solar filament. So what I'm talking about, these are star-forming filaments. So these are elongated structure of molecular cloud or the interstellar medium, which generally have aspect ratio, meaning that length to width ratio of more than 5 to 10, and they are significantly overdense compared to their background. So these are the general definition, and you already heard a couple of talks on these filaments. So before, so these filamentary structures of molecular clouds are known for a couple of decades, but the ubiquitousness of this filamentary structure only revealed when Herschel observation came in. And these are the example of nearby star forming regions. And you can see such filamentary structures are present in almost all galactic molecular clouds. So now these filaments are important because it is predicted that they are the host of most of the star forming cores, as it is predicted by several authors like Andre et al. In 2010, and also then Hakar et al. In 2011. So because they are believed to flow gas along their long axis and help in star formation. So this is the general belief. And also these filaments have the ability to form low mass stars. So in the denser parts of these filaments, the instability can occur, and that can gravitationally collapse, which lead to the formation of low mass star. And also, most of you are aware of that the problem in understanding the massive star formation is that how do they acquire large amount of gas in a short time scale? And their filaments also can help if such filamentary structure can create a common junction, which is known as hub. There they can carry the gas along their long axis, rapidly carry gas along their long axis onto that junction and create the favorable condition for the formation of massive star. In fact, such observational evidence has been found for such massive star formation. In one of our study in 2018, we found the formation of several massive stars in this central hub, which is located at the junction of at least 5 molecular filaments. And also recent ALMA observations have found subpersist filaments. They are carrying gas onto a common hub where massive star formation have occurred. So these are some importance of massive star. Now the question comes in one's mind whether these filaments have the ability. So we have seen, okay, they are carrying gas to protostellar, to core scale or to a common junction. So do they carry gas to the protostellar disk? This pointer is really disturbing. So if we want to find such a direct implication, whether filaments are really feeding the protostellar disk, So the implication should be we should find a correlation between the disk accretion and the accretion through filament. But life is really hard at that scale because disk accretion mechanism or disk accretion dynamics is tangled with the accretion dynamics of the molecular cloud, so which cannot be resolved even using the best facilities in the world available now. So, but still we have a solution, which is outflow. So outflows are also ubiquitous phenomena at the early phase of star formation. So this is mainly occur when accretion through accretion disk occur. So that gives the angular momentum to the central system. So some part of that angular momentum has to be taken away to stabilize the system, and outflow does that job to stabilize the system. So that means in all type of star formation where accretion through disk is occurring, we should see outflows. So, and these are bipolar outflows, so which are coming out of the polar region. So that means they are oriented perpendicular to the accretion disk. And these outflows are much easier to detect compared to the accretion disk, because accretion disk, it is mingled with the cloud dynamics, but outflows are much high velocity component. So they are generally found away from the central cloud velocities. So outflows could be a probe. So let us assume a conjecture that filaments are actually feeding the accretion disk or help in accretion disk. So these are the bipolar outflows. So if we assume that bipolar outflows are perpendicular to the accretion disk, then it should be ideally perpendicular to the filamentary structure. So this is the general conjecture we should now assume. And our expectation is that we should find a preferred orientation of outflows with their host filaments. So studies are performed with this belief. In 2017, Stephens et al., they reported a study using SML, submillimeter array observation, in Perseus molecular cloud. So they identified outflows using CO line, carbon monoxide line, and also the host filament using Atlas Gal images. And they found, here I have shown that, the random orientation of outflow direction with respect to their host filaments. So that eventually tells us that this is a low mass star forming region. So one may generally conclude that filaments are least important towards the protostellar disk or at that scale. But later, using ALMA data, Hongsu et al. In 2019, they studied on an IRDC, infrared dark cloud, which are younger massive star forming region. And there they found a similar study. There they found a perpendicular orientation of the outflow axis with respect to their host filaments. So that creates the kind of different scenario in different star forming region. This is massive star forming region. So we also performed a study using 11 massive clumps. Those are associated with ionized gas H2 regions. So H2 region meaning that they are much bit older than IRDCs. So we used high resolution ALMA observations, and we used this ALMA CO line to identify the outflows visually. So these are the typical outflows. You can see the red lobes and blue lobes are marked, and this is the host core that is driving the outflows. And we also identified the host filament using large scale survey, mostly 13CO survey, which help us to detect the cloud structure and which is not contaminated from the background or foreground clouds. So we identified the, I'm not going into the detail how we identified the filaments, but this is the filamentary structure, and ALMA field of view is embedded within this structure. So then we compared the outflows, axis of outflow with respect to their orientation of the host filament. And this histogram, cumulative histogram, I will ask you to concentrate on this black histogram. So this is the histogram of angles between the filaments and the outflows. So we wanted to compare this, whether this is a random or have some preferred orientation. But remember, this is 2D projection. We are seeing the sky projected angles. So these are 2D projection of actual 3D angles. So what we did, we simulated 3D angles, calculated their 2D projection, and then constructed this cumulative histogram and compared with our observed histogram. So here also you can see what we found. These are again random in nature. So there is no correlation at all with outflow axis and with the filament axis. So, but we are not convinced enough. So we wanted to continue further. So we have used now much larger survey, which is ALMA 3 mm observation of massive star forming regions, which is known as atom survey. So where there are 146 protoclusters are observed using ALMA. And now we have used SIO data. So this is similar to CO data, another tracer. So our recent observations don't include CO lines. So we use this SIO line for outflows, and we identified the outflow lobes. And also these outflow lobes are associated with 119 sources among these 146 sources. And this is the, again, histogram of the identified outflow lobes, orientation of outflow lobes with their host filament. And you can see the angles are distributed kind of all over, again, the random in nature. But probably here, what we were forgetting that our conjecture is the direction of gas flow, not only filament. So which filament we are seeing here, either the large scale filament or the dust filament, that might not lead or might not infer the direction of gas flow. So that's why we used the ALMA data itself to identify the small scale gas filament, which can infer the direction of the gas flow. So we have used this CS line, which is a cold gas tracer, made a moment zero map and identified the filaments. So then we compared in every region, we compared the angle between the filament and the outflow axis. And now we are getting a bimodal distribution. You can see some of them are parallel to the filamentary axis, some of them are perpendicular to the filamentary axis. So this bimodal distribution is actually saying that filament is probably important at that scale, because we are now seeing the direction of gas flow. So similar scenario has been observed before, but not in this aspect, outflow filament aspect, but in another aspect. In 2014, this Zhang et al. Reported SMA using SMA and JCMT observations. So they reported that the orientation of magnetic field and the major axis of the clump, they have this kind of bimodal distribution. So that tells that magnetic field have a crucial role in forming the star forming clumps. And also later, this JCMT Bistro survey, which Israel is part of. So there they studied the orientation of outflows with respect to the magnetic field. And there they didn't find any parallel, whether it is parallel or perpendicular, but still they found a preferred orientation, which is around 20 to 30 degrees. So that tells us that magnetic field also might help in gas flow, but the detailed signature is yet to be found. So this is in summary what we found, that filaments is probably playing a significant role in carrying gas onto the protoscalar scale, not only just hub or core scale. So this bimodal distribution probably saying that filament, the gas flow can occur along or across the filament. So that's why we are seeing the bimodal distribution. And also B field is important in star formation. So why bimodal? There could be some reason, like we should explore the surrounding environment, such as density, turbulence, and magnetic field orientation. For detailed study, we should look into that. So this is the summary of my work. As I mentioned, I want to say a little bit about the prospect of this kind of study using STAN-SPEC. So spectroscopic observation of these outflow lobes could be obtained using STAN-SPEC, and which could be helpful to construct hydrogen column density and temperature model. So most of you might be aware of this explosive outflow in Orion reported by John Bailey et al. In 2015. So there they observed, later on they observed in 2016, they reported the spectroscopic observation of some of these outflow lobes, or these fingers, they are telling these fingers using triple spec. This triple spec is exact configuration as it is in, for STAN-SPEC. This is associated with 3.5 meter telescope and have a resolution of 3500, so which is kind of similar to STAN-SPEC. So this kind of observation can be made, and these people use this hydrogen molecular line data to construct this temperature and column density map. And then they inferred how the environment is there towards these outflows and towards these sources. So which exactly could be done using TANSPEC observation for some of these outflowing sources where Harvey Harrow object is detected probably. So with this note, I'll stop here and thank you. So I have one point just to make. So probably we are hoping for our next star formation meeting in this big beautiful campus in Rationale National Center in Kolkata. And thank you.
Thanks for that excellent questions. Oh, sorry.
So nice talk. So I just have one question about this outflow and accretion thing. I mean, in your assumption, I mean, you are assuming that outflow is proportional to accretion, so on, and then explaining in massive star formation. So this concept comes of course from compact object what people have been doing earlier. So now problem here is that it depends on what spectral state is your disk. So if you assume the standard disk, thermal state and so on, nicely can be explained. But now problem happens in far away region is how do you know if you assume that it's geometrically optically thin disk, it's very difficult to make outflows out of it. So question is that how do you find geometrically optical thick disk? So have you, I mean, your sample, how many sources are there? Can you talk about
we have so although these are massive star forming region, we have identified mostly low mass star forming cores. Those are driving outflows. So we don't have much information about the accretion disk. So only we have seen that outflows they are associated with those cores, and then the filaments. We compared this for this study.
So I think what you mentioned about TANSPEC, that will be interesting if you can identify the line tracers.
Yes.
And prove that these are the thermal emission coming from
this
line ratio and so on. Then it gives a really solid piece of this to explain this.
Yes, that is perfect. Yeah. Thank you.
Manoj,
Nice talk, just you probably are aware of another word where people are looked at this outflow direction and the magnetic field direction. Magnetic field direction, both large scale and small scale. Large scale from optical polarization measurements and small scale from sub-millimeter polarization measurements. And what they find is quite interesting. At the small scales, there is some correlation in the sense either for period, but large scale, it's all over the place. So in your filament direction as well, the newer study of filament direction and outflow direction, do you see any such trend?
Yeah, that's what actually I presented.
So CS is small scale.
CS is with ALMA data, so that is really small scale, like sub-parsec scale. Sub-parsec.
Sub-parsec.
Yes.
Yeah, I think
so there we find correlation, but parsec scale we didn't
I think
find
it's very
anything.
similar in the polarization.
Yes.
I was just curious about that bimodal distribution of lobes. So in that bimodal distribution, you said number of lobes. So did you, like if you saw the blue and red, did you count them as two separate?
Yeah, two separate, not single.
So, yeah, so wouldn't it be, because then directionality, there is some issue, right? You can just take one of the lobes.
Okay.
And that will give a more statistical thing, because if you're counting two lobes, then there will be double counting on those directions.
But there will not be any change in distribution, right?
No, but some may be only single lobe.
Single lobe also we counted as outflow.
Yeah, but some are single lobe and some are double lobes. You have double counted each lobe twice.
Yes. Each, not each lobe twice. Outflow, blue lobe separately, red lobe separately.
Yeah, so if there's only one lobe from one outflow,
statistically, you are saying.
yeah. Maybe you can just have a look at that.
Final question. Yeah, so this is a very, so you showed this bimodal distribution where you are not showing cumulative plots, which you showed earlier.
Yes.
So why two different ways of presenting?
There is no reason for that.
So suppose earlier.
Here it is easier to visual.
I understood.
Yes.
So earlier case, if you had made similar plot, would it have really looked noisy
No, no,
flat?
Yes, that is flatter. A small peak. Okay.
Because cumulative can hide some detail.
A small peak in this 10 to 40%, about 10%. So
no, was there
like flatter only?
Any reason driving why only cumulative are displayed in this case?
Earlier, actually, we wanted to compare with the previous studies, like here. So that's why we got it. That work is published. But now what we found, it is easier to show bimodal distribution is easier to show only with this
was
program.
it sample size or something? If you have very small number, then
No, not
okay, thanks.
How dynamic these filaments are? They vary with the time.
Oh, difficult question. No, not much. No, not much observations actually.
You can tell what is typical dynamical time.
Typical, these are million. Yes, million.
Yeah.
Too long. Okay, thanks everyone. Thanks for that interesting talk. The next speaker is Naval Badri. He is from PRL. We'll be talking about discovery of new X collapse candidate filament in massive star forming sites. So you have 15 minutes.
So good afternoon, everyone. First of all, I thank organizers to organizing this offline meeting and giving me opportunity to present my work here. So in this presentation, I shall be presenting the results of our recent works, where we found the results of related to the role of filaments and star formation. These are my collaborators, and I am a fourth year PhD student working in here. So this is the outline of my talk. I will briefly introduce filaments and the role of filaments in star formation. Although you have understood a little bit about filaments in previous talks, then I will be specifically talking about one of the physical process of star formation in filaments, that is known as the end-dominated collapse. And then I will present the observational results where we found the end-dominated collapse candidates. And finally, I will summarize my talk. So the interstellar filaments are the elongated structures of gas and molecular gas, and they are widely their sizes widely ranges from protostellar envelope to the cloud scale, or maybe giant molecular cloud scale. So in the scale, they can vary from like sub-parsec scale to the 10 parsec or more, maybe 100 parsec or so. They are widely observed in multi-wavelength ranges, ranging from optical to longer wavelength, like millimeter wavelength. So in the optical wavelength, these structures appear in absorption features, while in the longer wavelength, they become prominent in emission. And since these structures are generally associated with the star formation activities, like they host the H2 regions, which are the observational signatures of massive stars, then embedded clumps and the clusters of young stellar objects. So the obvious question is that what is the role of filaments in star formation? Like in the bottom images, I show different configurations of the filaments and where they are playing a role in star formation processes. So all these images are the column density maps, and where here you can see that there are different structures. One, we can identify isolated filaments, like the left one, which is Sh-242 filament, where you can see the nice elongated filamentary structure. And you see some dense high column density regions along the filamentary structure. And in the bottom region, you see some multiple filamentary configurations, like where several filamentary features are seen. And in the right panel of the middle image, you see filamentary structures, which are generally converging into the central region. So in the central region, the density is higher. So this kind of configuration is known as the hub filament system. And it is also possible that at least two filaments, they can play a role, like they can couple to each other, or they can collide. So it could be a case of like filamentary twisting, as you have heard in previous talk, and some colliding filaments can play a role in the star formation process. Like the bottom image you see is the column density image overlaid with the two filamentary cloud shown in the red and blue contours of molecular gas. So the question is that what are the physical processes responsible for star formation filaments? Although, as I mentioned, that there are different configurations, so people actually studied these configuration independently in different studies. So I will be specifically talking about the N-dominated collapse process and filament. So first, we need to identify filaments. So these structures, as I mentioned earlier, can be obtained from the dust continuum maps and molecular maps also. But to identify some isolated filaments, we need to have another information, that is the velocity information. So in the position velocity space, these filamentary structures can be distinguished clearly. Like you see here in the image that the different color structures show the filaments in different velocity structures. So although, as I mentioned, that filamentary features are elongated structures, but generally they have some not very regular geometry. So they have some, in real life, they have some irregular geometry. So to simplify the calculations, previous theoretical studies considered filaments as an elongated isothermal cylinders. So in this case, the gas pressure that is balanced by the gravitational pressure, and such kind of configuration is balanced in this case. So the filament, this is the cartoon diagram, can be considered as a filament. And the gravitational instability of these structures generally identified or studied by the critical line mass parameter, which is generally depends upon the gas temperature. And one can compute whether the filamentary structure is gravitationally unstable or stable. So when we measure the observed line mass, like we calculate the mass of the filament and take the ratio with the line length, and then we compare with the critical line mass. So if the line mass is greater than the critical line mass, then these filaments are considered as critical filaments, and they are unstable, so gravitationally unstable, and they fragment and they collapse and fragment to the core. In the previous talk, you saw that in the filaments there are several like dense cores can be formed in the filaments. So they are generally there are different collapse mode of the filament. Like when the filament collapses radially, so it is found that the filaments collapses and fragments into the several dense cores along the filaments, and they form the low mass stars. But there is another physical process that is the N-dominated collapse process. What happens? This is generally you can consider the collapse, the similar collapse model of a spherical cloud. So in this case, actually the gas motion along the filament is considered longitudinally only. So the recent theoretical studies, they calculated the acceleration of the gas inside the filament, and they found that this acceleration is dependent on the relative distances, which is measured from filament center to the outer side. So this acceleration is generally, we can say, the aspect ratio dependent, and at the edges the acceleration becomes very high. So as you can consider that the gas motion, which the gas particle which are at the edges, so they generally try to move inside because the acceleration is high at the edges. So they impart momentum and they generally sweep up the material which is just inside of the end gas layers, and in that way they actually form the dense region at the edges. And in some cases, they collapses locally at the edges compared instead of showing the global collapse. Global collapse, I mean that these two edge clumps, they collapses at the center. So this collapse time scale is generally that is called as the collapse time scale, and this depends upon the aspect ratio. And when we compare this to the collapse time scale of the spherical cloud, so we found similarity, like it depends upon the initial gas density, but there is a difference, like for the case of the filament, this collapse time scale depends upon the aspect ratio. So here there are two profiles, and these are obtained by the numerical simulation of the filamentary evolution. Like they have tried to study the global collapse of the filaments, and these profiles are obtained at the time snapshot of 0.55 million years. And you see there are two profiles, one is in green and another one is the blue one. So for green, this is obtained for the filament with having aspect ratio of 10, and the blue one is for the filament having aspect ratio of 3. So the top profile is the volume density profile along the filamentary axis. So in this at the snapshot of this time scale, what Clark et al. Found that at the edges the density increases, and these could be the observational signatures of N-dominated collapse. Simultaneously, we should see the velocity, like we should see the velocity profile like this. But this is only for the case like when we see filamentary axis along their longer spine. Like when we observe filaments from this left side, then the edge clumps which is at the left, this is moving into the central region, so it should show some rate shifted peak in the velocity, and the another clump which is moving to the center, that is show the blue shifted peak. So these are the observational signatures of the N-dominated collapse. So to study the such processes and to explore other physical processes in the filaments, we have identified two sites in the monoceros and Aquila constellation. So here in the left one, you see a three-color composite image of monoceros complex, and there is a famous monoceros Obion complex, and the near one, which is in encircled, that is the monoceros R1 region, which is our target site, and this is most nearby target site located at a distance of 760 parsec. And the another target size is located at 8 kiloparsec, and this is in Aquila constellation, where there are two major star-forming complexes, G45.49, which we call as a G45 East because it is in galactic east direction. Another one is the G45.14, that is in the galactic west direction. So in the monoceros R1 region, we have studied the velocity profile which is obtained from the Fusion 13CO line data, and we found that this region consists two velocity peaks. When we studied the moment zero map, which is basically the integrated intensity along the spectral axis that gives the cloud structures. So we found that one of the peak is associated with some elongated filamentary cloud, and so this cloud we call as a monoceros R1 filament, and another one is obtained as a diffuse cloud structure. And when we did the literature survey, we found that the filaments edges is associated with two star-forming sites, IC446 and IC447. And in the similar case in Aquila constellation, we see a velocity profile similar to previous one, but we have modeled with this Gaussian profile, and for the major Gaussian component, we have obtained this moment zero map, and we see the elongated cloud structure. And we can also study the velocity field to confirm whether these structures are velocity coherent or not. So we see that these structures are velocity coherent, means these are the single isolated cloud, although we see some signatures of velocity gradient at the edges. And these could be the signature of the accelerated gas motion as predicted by the N-dominated collapse process. So to study the physical properties and the star formation activities, we use molecular line data. We use photometric and continuum line data, continuum data from the near infrared to far infrared, and we generally study the column density map, which can be obtained from the dust continuum maps from Herschel and can be obtained from the molecular line data as well. So the left one is the column density map for monoceros R1 filament. You see there is a nice filamentary structure, and there are some dense regions along the filaments as well. we estimated the mass of the filament around 1500 solar mass. And for this, the cloud in the Aquila constellation, we calculated mass that is around 1 million solar mass, and the length is around 75 parsecs. So based upon the physical properties of this cloud, we named it as a giant molecular filament G45.3 plus 0.3. So, and we have also identified the young star objects, and we saw the distribution of these structure, young star formation activities. We calculated the stellar density for these young star objects, and we overplotted the stellar surface density plots over the dust continuum and the molecular maps. From here, we see that the star formation activities are mainly dominated at the edges compared to the central regions. This is the observational signature of N-dominated collapse process. So in this way, we were able to say that the N-dominated collapse process is ongoing in the monoceros R1 and the giant molecular filament, and this is responsible for the formation of the star forming regions at the edges. But as I mentioned previously, that there are different physical processes, and people have independently studied these processes. But in our recent work, in the case of giant molecular filament, for the first time we found that both the physical process like N-dominated collapse process and the presence of filament systems are simultaneously seen. So the bottom image is shown the Herschel 160 image of the molecular cloud or that region, and you see some nice filamentary structures there. We identified these filamentary structures from filament finder tool, that is the GetSF newly developed tool. And here we can see that there are at least 3 or 4 filaments which converges to the central region. So in each of the dense region, these filament systems are present. So when we compare when we see that how many N-dominated collapse process candidates are available in the literature, so there are very few in the literature, and even out of them, very few number of them are really very convincing. Like the one is NGC 6334 filamentary cloud. The top one shows the dust continuum map, and it shows some nice dense clumps at the edges also. But the bottom one shows the velocity map, which presents that there is the velocity gradient along the filamentary axis, which is generally moving from edges to the central region. And there is another case, that is the Musta cloud. So this shows the nice elongated filamentary structure, but at the edges the fragmentations are higher compared to the central region. So these people have speculated that these could be the N-dominated collapse candidates. Yeah, I have something else. Yes. So other filament, the candidates are G341, and another one is S242 filament. And in S242 filament, you see that at the one of the ends there is a H2 region. So in this way, we can see that the H collapse process can be important in terms of the formation of massive stars. So in summary, as I mentioned earlier, that the filaments are very important to study the role to study the star formation process. And when we study the H collapse process, so there are observational signatures that at the edges we should see high density regions, and we should also see some velocity gradients. And in our recent work, we found that in the giant molecular filament, we found that for the first time, it could be possible that both the physical process like N-dominated collapse process and half filament configuration can simultaneously occur. That's all.
One quick question. Okay. Yeah.
Thanks, Naval, for this nice talk. But your slide, you have shown a simulation where the aspect ratio is depending on the aspect ratio, the gas flow changes.
Yes, acceleration.
So what is that? What is the driving? What does that drive that? Because filament weight is fixed.
Yes, sir. Generally, this kind of collapse process is only gravity driven only. Like as we compare to the like spherical cloud geometry. So we consider that in initial condition, like it is in balance, like thermal pressure balances by the gravitation. But if there is some perturbation, so that like in the spherical case, the cloud collapses. So in the similar case, in the filaments, the edges, the gas motion actually, that is the only point, like the gas is allowed only in the longitudinal axis. So in that case, only gravity is the driving factor for that motion.
Thanks. Let's thank Naval for that wonderful talk. So next speaker is Sri Lakshmi. She's from ISC and she will be talking on about thermal and non-thermal emission of protostellar jets. You have 15 minutes, 12 plus 3.
Good afternoon, everyone. First of all, I would like to thank the organizers for providing this opportunity. And today I'll be discussing about an emission model for protostellar jets developed to calculate the radio spectrum by incorporating thermal free emission and non-thermal synchrotron emission. So in my talk, I'll briefly talk about protostellar jets and about the motivation and the model which we have developed in brief and summarize the results. So protostellar jets are seen in the early phases of star formation in which matter is actively accreted, and these help in carrying away excess angular momentum and helps in further accretion of material. So shown here are the various sequences of evolution in the early phases, starting from molecular cloud collapse and the collapsing cold core phase, then in the hot core phase, and finally in the H2 regions. So of these phases, protostellar jets are associated with the hot core phase, which is also associated with the accretion disk. It is this accretion disk along with the magnetic fields that play a key role in the launching and collimation of jets. It is because the accretion disk helps in bringing material closer to the accreting star, and the materials can flow along the magnetic field lines and hence can be launched. Based on the distance at which the launching of materials happen, two models can explain this whole process, which are the X-wind models and the disk-wind models. According to X-wind models, the launching happens very close to the star, roughly 0.05 AU, and in the case of disk-wind models, it can happen up to few AUs. Now, our motivation is to characterize a radio spectra of these protostellar jets. An existing widely used model for jets is the thermal analytical model of Reynolds 1986, which calculates free emission from narrow collimated jets. And shown here is a schematic diagram of the Reynolds model. But the Reynolds model has various assumptions, such as it's only applicable for small angle opening angle jets, and also assumes that the base of the jet is completely optically thick and the outer regions are completely optically thin. However, observations have shown signatures of non-thermal emission along with free emission. So our model has more generalized geometry that is applicable to wider opening angles, and we include intermediate optical depth in our calculations, and also we incorporate free and synchrotron emission in the calculation. For example, shown here is HHA 8081 jet, which is one of the prominent jets which have shown non-thermal emission in the spectrum. And shown here is a spectral index map of the jet. A spectral index of flatter than -0.1 is considered as thermal, and the associated emission mechanism is free radiation. And shown here is a typical spectrum of free radiation. On the other hand, spectral index of steeper than -0.1 is non-thermal emission, and the contributing emission mechanism is synchrotron radiation. And shown here is a typical spectrum for synchrotron radiation. And here it can be noticed that for this jet, the central region is dominated by thermal emission, and the farther regions, especially at the edges of these knots, there is more dominant synchrotron emission. This is because the jet impact the ambient medium. At these edges, strong shock formation can happen, and at these shocks, particles can be accelerated to relativistic velocities, thereby resulting in synchrotron emission. So we have kept in mind this geometry while developing our model. So shown here is a schematic diagram of the model. This is a side view and front view as seen by the observer. So the basic structure includes a highly ionized free emitting region in the inner region of the jet close to the axis. which is surrounded by a shocked region, which is shown in the shaded portion. This emits both free and synchrotron radiation. So for this jet, the jet injection radius here is R0, and for this jet seen in the plane of the sky, the projected length is represented as y. For any y, there will be a corresponding radial distance measured along the axis of the jet, which is Ra, which will determine the properties of the jet. So the y projected length and the radial distance are related by the inclination angle of the jet, which is given by this equation. And we assume that all the parameters such as the width, opening angle, ionization fraction, and number density vary radially, given by this power law relationship. Shown here is for width. For example, W0 is the width at the jet injection radius, and epsilon is the power law index, which determines the geometry of the jet. So only for ionization fraction, we have also considered lateral variation along with radial variation. This is because for certain sources, it is seen that the ionization fraction is highest towards the axis of the jet and it drops towards the edges. Shown here, for example, is a DG tau jet in which H alpha emission is observed. So here, high velocity the gas is seen to be collimated close to the axis, and as we move to lower velocity, the opening angle appears wider. So since we believe that ionization is a result of shocks and the strength of shocks depends on the velocity, we assume that the profile of ionization fraction is also similar to the velocity profile. So in our model, we assume that for any point located along the line of sight, which is, for example, a distance of s from the axis, we assume that the lateral ionization profile follows this law, such that Xa is the ionization fraction along the axis, and the profile will depend on the distance of this point from the edge as a fraction of the total width of the jet at that point. So for overall, for any line of sight passes through two layers of shock material, which emits free and synchrotron emission, and the inner region that emits purely fixed radiation. And it is to be noted that the source function, which is the J nu and alpha nu in both of the shock region and the purely fixed region are different because of different emission mechanisms. So overall, for any given line of sight, we calculate the overall intensity by summing up the contribution from all the three regions. And this intensity is what we integrate over the entire length to calculate the total flux density from the jet. And we use this to construct the spectrum of the jet, and which is a function of different jet parameters. Next, we look into the effect of jet parameters on the overall spectrum. First, we look into the case of fully thermal jet. So the most important parameter is the number density. Shown here is a number density profile of the jet, and this cartoon diagram shows how it varies radially. It will be higher number density at the jet base, and it falls as we move radially outward. So the plot shown here first is for the number density at the jet injection radius. It is intuitive to understand that as the number density of the contributing particles increases, the flux density correspondingly increases, which is seen in the plot. The next parameter is the power law index of number density distribution, which is Qn, which determines the steepness of the radial profile of the density. As Qn increases, the number density profile becomes steeper, and which means the overall contributing particles will be lower. Therefore, the flux density also decreases. Next, we look into the jet injection radius R0. For this, consider two jets with two different R0s. From this equation, given that Qn is a negative quantity, we know that as R0 is higher, the number density at any radial distance will be higher for a jet with larger R0. This is also understood from the plot. Next, we look into the effect of jet parameters on the synchrotron emission. For this, I consider a jet with both thermal and non-thermal emission and located slightly farther away. This is to replicate outer knots seen in jets. So the effect of number density, Qn and R0 are similar in this case. So here we look into synchrotron exclusive parameter. For example, is the magnetic field strength. Here also it is easy to understand that as the magnetic field strength increases, the efficiency of acceleration of particles to relativistic velocity also increases, and hence the flux contribution will be higher for higher magnetic field. Here delta theta is another quantity which determines the thickness of the shock region. So again, as the thickness of the shock region increases, the flux density also correspondingly increases. Shown here is the number density profile in energy space for the non-thermal particles which emit synchrotron, and the power law index P represents the distribution index. And as P is increased, we can see that the distribution will become steeper, which means there will be a lower number of particles at higher energies. Therefore, for increasing P, the contribution flux density will also be lower. Next, we look into the evolution or the transition from thermal emission to non-thermal emission in a single jet. For this, I keep the main jet parameters constant and vary the relativistic fraction of electrons present at the shocked regions. As relativistic fraction equals 0 implies it is fully thermal jet, which is shown in the red plot. And as eta is increased, the synchrotron contribution correspondingly increases, and until synchrotron emission dominates the whole spectrum. So this shows that relativistic fraction of electrons can regulate the contribution of synchrotron in the overall jet spectrum. So after this exercise, we have understood how the parameters influence the jet spectrum, and with this knowledge, we have tried to fit the models to various sources for which non-thermal emission was observed. I show one example here, which is HH8081 jet. Here the central source is IRAS 1816-2048, and the outer knots have shown a non-thermal emission in their spectrum. So the central, we get two scenarios within the same jet. The central region is dominated by thermal emission, and we choose one of the jets here, which shows non-thermal emission dominant spectrum. In both the cases, the dashed line and the solid line shows the fits for two different epochs. This is because the source is shown to have variability, so we have fitted separately for two epochs. So our model fits well for the 2012 and 2018 data for the central jet, and for the 1993 and 2018 data for HH81. The table here shows the best fit parameters for both the knots for two epochs, and these are the chi-square values for the fit. And we have followed the same procedure for various jets in which synchrotron emission was seen, and these are the various sources, and these are the best fit parameters which are obtained from this calculation, and these are seen to correlate or similar to the observations which we have seen towards these sources. So overall, we have developed a model to explain the steep spectral indexes, negative spectral indexes seen by including synchrotron emission along with free radiation. And also we have made an improvement with the previous analytical model by including a geometrical generalization and optical intermediate optical depth calculations. Then we have analyzed how the spectrum behaves with various parameters of the model, and with this knowledge, we have fitted the model with sources and calculated jet parameters, which are found to be consistent with the observations.
Excellent work, Srilakshmi. I have a couple of questions about the model. Do you account for free self-absorption? You know, in the low radio frequencies, self-absorption is a major.
So in the shock regions, we have taken free plus synchrotron and the absorption corresponding to that. Both free, I mean, we have taken absorption coefficient as the sum of free absorption plus synchrotron.
So there is self-absorption taken. The other question I have is in the cartoon which you showed, you probably showed the shock region as shaded, and then inside is unshocked. But then you assume that is ionized already.
The inner regions will be ionized because of internal shocks. But
so
not,
they are also shocked.
Shocks are there, but not strong enough to. We assume that the shocks at the edges will be strong enough to accelerate the compressor magnetic field and then accelerate.
But the inner region is also ionized.
Inner region is also highly ionized. The region will be the ionization fraction. We have assumed that it is falling from the axis towards the edges.
I see. Then why don't you have synchrotron emission?
The compression of magnetic field has to be strong enough to accelerate, or the amplification of magnetic field should be there. But that is happening where the stronger shocks are happening.
Why do you say stronger shocks are happening in places where the ionization fraction is lower than?
No, because stronger shocks, I am saying because.
Wouldn't you normally expect the ionization fraction to be high and the compression of the shocks to be?
We assume this because the jet is impacting with the ambient medium, which is at rest. So the impact would be higher in the region where it is interacting.
Okay, we can have one more question, quick question if it's there.
I think it's a very similar question. Always, so how many sources you have where you have found this thermal and non-thermal emission in the outflow?
So I have fitted for 5 sources.
So in literature, only 5 sources are available, or
no prominent sources we have. This is not a that work which we have done is not final. That was just it's not a rigorous fitting.
Yeah. Why I'm asking that always, because always you are assuming that the inner region there is a free emission on this. That is the case everywhere, or it changes?
It's not same everywhere. It's the
So
same.
whatever sources you have shown,
Those sources have shown
on
non-thermal emission.
Yeah.
Okay, thanks. Let's thank the speaker for their wonderful talk. And, we have a final speaker for this session. Yes, speaker. It's Kshitij. He'll be talking about the CO view of a hub filament system in the outer galactic plane. You have 15 minutes.
So I'm going to talk about CO view of SS2138 region. It's a distance greater than 5 kiloparsec hub filament system in the outer galactic plane. So we have already seen a lot of talks about the hub filament system, but let me motivate it in a slightly different manner. So the primary motivation for why we study hub filament systems is that high mass star formation is not very well understood. And there are various reasons for it. As we know, they are faster evolution time, rarer occurrence, farther distances. In general, they are found greater than 1 kiloparsec distance. For low mass stars, the sequence of evolution is generally well known. Like there is class 0, class 1, class 2, class 3, then the main sequence star. But for high mass stars, the sequence is not well known because the star reaches the main sequence before the accretion has finished. However, there is an empirical sequence of high mass star formation which has been established, which has been put forward rather by many authors. And a broad overview of that empirical sequence would be something like, in the initial stages, there are infrared dark clouds or massive cold molecular cores or massive starless clumps. These could be various names for the same object, but various authors have put forward these names. Then they evolve into high mass protostellar objects called HMPOs, protostellar massive dense cores, hot molecular cores, and finally the H2 regions, which again evolve from compact to classical. So what we are interested in is something called IRDCs, infrared dark clouds. So here's an image from Motte et al. On the left, you see a Spitzer image in MIR. So what you see, these dark patterns, these are the infrared dark clouds. And on the right is the H2 column density map. So these patterns can also be seen in the column density map. So this is seen in absorption against the mid-infrared emission from Spitzer. Now, it has been seen that the IRDCs which are observed in mid-infrared are seen in emission in far infrared. And many of these IRDCs resemble filaments which merge to form these hubs, which has already been talked about and you have an idea of by now. And the classification of the structures into these categories, hubs and filaments, is based on the criteria like aspect ratio and H2 column density. For example, for the hubs, the column density should be greater than 10 to the power 22 per centimeter square. That is the criteria of Myers 2009. This is a standard paper which is quoted for the hub filament systems. And these are some of the regions, common regions, which have been like, which show very popular, like which show the hub filament system, very common. So like this is a PAX 160 micron image of a W40 region. It shows these filamentary structures merging into a hub. On the left is the IRAS 16148 region. It's a column density map, but again, you see these clumps connected by weak filamentary structures. And in the center, this monoceros R2 region, column density map in red. From Trevino Morales et al. Again, you see this hub filament system, and on this image is a schematic of the hub filament system of monoceros R2. The W40 region we can see is a slightly evolved region because the OB stars which has formed in the center has blown away the entire region because of its output of Lyman continuum photons. So you don't see a very prominent hub structure. In fact, it answers one of the questions which was asked whether the hubs the filaments evolve dynamically. They don't. The evolution time scale might be large, but they can be affected by the OB stars which output a huge amount of matter and radiation into the interstellar medium. So with that, I come to the SS2138 hub filament system. This is a multi-wavelength view from Tapas et al. 2015 paper. You can see that the cluster which is seen in near infrared and mid infrared, as you go into far infrared wavelengths, you start seeing these hub filament structure. So it's a galactic plane object in the outer galactic plane, and it's one of the few regions. I couldn't find many other regions which is at such large distance of 5.7 kiloparsec. It is an associated IRAS source, IRAS 22308 plus 5812, and it has 4 trapezium-like stars near the cluster center, near the IRAS source. So that makes it interesting that OB stars forming at the center associated with the IRAS source in the outer galactic plane. The data used by me was to give a brief overview, CGPS 12CO data and JCMT 12CO, 13CO, C18O data, 322 transitions were used, and CGPS 12CO 120 transitions. Other data which was used for examination of morphology, calculation of mass, etc. were Herschel FIR images and Via Lactea for column density map. So this shows the brief morphological overview of the region. From left to right, you see the CO322, 13 CO322, C18O322. So the increasing critical density. So each molecule, as you go towards the right, probes denser into the medium. So in CO322, for example, you see the diffuse emission. From in 13 CO322, you see these filamentary structures coming into picture. Then in C18O, you only see the clump, central clump. The main takeaway from this figure is that in the velocity, in the M1 map or the velocity map, what we see is along the filaments, there is higher velocity. So if you focus on 13 CO map, there is higher velocity along the filaments, and in the center, the velocity is lower. So there is some kind of velocity gradient, which will indicate some kind of longitudinal flow of mass along the filaments. Another takeaway from here is in the line width map. If you focus on the 13 CO line width map, in the center, the line width is higher, and along the filaments, it's relatively lower line width. So this indicates that the gas is coming together from the filaments and merging into the central hub. So this could indicate that the gravity, well, the OB stars forming there, the cluster forming there is accreting all the matter. But like that needs additional evidence, but this could be an indication. So this figure, if you focus on the figure on the left, this is the CGPS 12CO120 integrated intensity map. It's a huge region, about 100 kiloparsec across. But we took the spectra of each of these peaks in the 12 CO, and we found that the entire region is not SS2138 hub filament structure. So it could be, this could be because of projection effects and some and other such things. The main hub filament structure is in the center.
And this hub filament structure, so in the center, we take the Herschel 350 micron image. And with the help of my collaborators, we use this software called GetSF software from Menschikov et al. And we run this GetSF software on the 350 micron, which indicates the thermal dust emission, the cold dust emission. And this is the filamentary structure we get. The other layers like this part, and they are outside the field of view, and they are separate filaments. They come out as separate filaments, as was expected. Next thing, so if I zoom into this center region further, here, the magenta contour show the this column density contour 10 to the power 22 per centimeter square. So this is the central hub according to the classification criteria of Myers 2009. And the interesting thing here is that the background image is JCMT 13CO322 integrated intensity map, and the blue line and the red line are the outflow lobes from Quinn et al. Paper. And the green in this image, the green lines are the filamentary skeletons from the previous image. So what is to be noted here is that the outflow lobes are along the filaments which were detected. I'll come back to this later in some time. And this blue dashed circle is the peak of the blue outflow lobe. It is not, as you can see, associated with the IRAS source, which is the magenta cross, and the high mass stars are here. The blue outflow lobe is separate. So in the zoomed in central region, we try to see if we can identify the filamentary structures. First thing is the overall filamentary structure. Then in the zoomed in central region, we try to see what kind of structure we get. And we constructed the channel map. The main takeaway from here is we see three filamentary structures. Which we have named SEF, southeast filament, the western filament, and the southwest filament. So once we identify these three filamentary structures, the next thing we did is to take spectra at various points, the various peaks. So on the left is 13CO322 integrated intensity map. On the right is 250 micron Herschel image. So you see that these two images are very well correlated with each other. As in the peaks which you see in 13CO322, you see the almost similar peaks in 250 micron. 250 micron has some extra dust peaks, but we took spectra there also. And the main conclusion we found from the study of structure, I will not go into details, but these are the main conclusion, that they are, apart from the hubs and filaments, where the filaments join the hubs, there could be secondary filaments. These secondary filaments join the main filament, often called the primary filament, and the primary filament then joins the hub. And what we found is there could be velocity gradient between the secondary filament and the primary filament, and the primary filament and the central hub. So there is gas flow occurring all along. Then we calculated the physical parameters like filament line mass, the southeast filament, this C14 along this length was found to be transcritical, and we also so it was found to be transcritical, and there is also a C14 source forming here, which can also be seen in the Herschel image. So it goes well with our conclusion. Then western filament and southwest filament were found to be subcritical, which is along this filamentary length and along the C6, C7 filamentary length. And we don't see any starless cores there or any peaks there as such. So that also tallies well with our conclusion. And then we calculate the Mach number and non-thermal motion. There was dominance of supersonic and non-thermal motions there. Normally, supersonic and non-thermal motions in text, you will see is a combination of some kind of magnetic field activity. So that is something which needs to be investigated in future. Yes, it's almost. So this was the main analysis which was done. Now, I again bring you to this figure. This is the JCMT 13CO322 integrated intensity map. And as I mentioned earlier, these are the lobes, outflow lobes, blue and red outflow lobe. And the peak of the blue outflow lobe is correlated with one of the Herschel clumps and even 13 CO clump we saw earlier, C14, which was labeled. So is it a massive source? That needs further investigation. Then second conclusion, second thing we need to investigate further is that it has been seen in text that the outflow can form shells, and these shells could be mistaken often for filaments. So could it be that these outflows are leading to formation of shells, and these shells are being mistakenly identified as filaments? Since high mass stars, OB stars, drive a lot of outflows, and there have been few talks about the identification of filaments near the OB stars. So we need to take care that we are not mistakenly identified these outflow shells. Then the third thing is that in the central region, in the CGPS 12 CO spectra, we also see two peaks, and these two peaks need to be investigated for further, because it could be that there could be two different clouds in the line of sight. So could there be some kind of cloud-cloud collision happening? Because it has been seen in many papers that cloud-cloud collision is believed to be responsible to be formation of hub, and also filament-filament collision can also happen, which can lead to formation of high mass stars. Finally, as I said earlier, one of the conclusions that we need to study the impact of outflow on turbulence and supersonic motion. And so this was the analysis which I have done, but this analysis raises more questions than it answers, and it could be a subject of further study. But as of now, this study has been like under review in ABJ. So I hope to investigate this further in future.
One or two questions?
You mentioned about the distance. So did you measure that or you have taken?
No, I've taken it from published literature.
It's based on which?
It's based on kinematical models, the rotation curve of the galaxy.
So like, did you check with Gaia?
No, Gaia I have not worked with. But I don't think it's there. Like if you see the survey, do a survey of what all distances are published, I could not find Gaia coming up in the search, but I'm not sure. I have not searched specifically in the Gaia.
This is last question.
So in those stars which are formed in the secondary filaments versus primary filaments, do you find any statistical difference?
So the secondary filaments are kind of outside our field of view, just barely connecting. But we can infer secondary filaments because other regions like Monoceros R2, they have also indicated secondary filaments. So they could be that. So, but it's outside our field of view, and we have not done a near infrared study of young stellar objects.
So in general, do you expect probably low mass transformation in the outskirts when compared to the primary filaments? What is the general scenario?
Can you repeat the question?
In general, the secondary filaments, those stars are formed in the secondary filaments. Do you expect them to be low mass, preferably low mass when compared to the main?
That's a very hard question. But low mass, see, high mass star formation, you need some extraordinary condition. In general, you would expect low mass star formation only, unless there is some heavy gas flow or collision of objects, collision of clouds or some such things, or filament collision. Generally, you would expect low mass star formation only. You would expect high mass star formation.
Let's thank Rcw for the session.
I have to make one announcement. So those who are going to Devastal, they have to confirm their journey to Rationale IST. And if from Devastal, if they are going to railway station, that also we need some that information by today. And for those who have claiming traveling allowance, so they have to give their bank details also in the form. So shall we meet at 2 or 2:15? 2:15. Yeah. 2:10 maybe. Because we have only 15 minutes. Yeah, between unfolding talk and. Yeah.
I made some changes. They will love it. हाँ, उसमें तो मेरा भी पूरा है। लेकिन दवाई है ना। Last time मेरे को तो पूरा हो गया।
Which one?
The N वाला, हाँ, the first two. With N, no? हाँ, which has serpent's N, no? हाँ, correct. But Amit, you should take them. Because they will remember it all sides. है ना? I mean, you have anything against? Problem है क्या बच्चों को लेके जाना? नहीं कोई दिक्कत नहीं। But क्योंकि उन लोग, I know people, older people, उनको lifelong याद है। मैंने वो देखा था। Personally, मैं किसी से मिली थी, उसको कहीं and that lady is a doctor gynecologist. And both my children, she only got them out. And अभी भी वो कब मार्च का कब था 2010 में कुछ था ना long time back. She still remembers. I was shocked.
हम लोगों के लिए शायद इतना इम्पोर्टेंट नहीं है लेकिन जो स्टूडेंट में नहीं है
उसने कभी नहीं देखा है ना फर्स्ट टाइम व्हेन यू सी इट हम छोटे 6 इंच ही बताते तो बच्चे विद द एन वाला ना या one slide I've added. Yeah, open the PPT. अरे you put serpents, you didn't take serpents N. PPT is वो वाला ही है. आपको should I put it in here? See the नहीं, this is PDF. उसी में देखिए आप. Go back to the pen drive. Pen drive में हाँ.
This one. PDF.
हाँ.
Other one,
अच्छा नहीं, it is serpents ही है. अच्छा, there is no N इसमें नहीं है. तो शायद वही ठीक है. नहीं, just open it ना. Open it. हाँ, this is fine, correct. ठीक है. Can I put it up? Yeah, अभी नीलम है, after नीलम. नहीं, वो सुबह मैंने लगा दिया था भाई, फिर कुछ चेंजेस किए. वो बैठे और हाँ, वो फील अरे ये एक और चीज डाल देना है. हाँ, वही कितने हैं स्लाइड्स में? हाँ, नहीं पर वही थोड़ा रिवाइज करते हैं. बट ये तो गाना अलग ही था जिससे बात आ जाना. I mean the jets and outflows and outflows. हाँ, वही मेरा गाना अलग है.
अच्छा
मैडम आप उस कॉर्नर से
नहीं मैं तो इधर से
नहीं, ये आपको माइक जो लगेगा ना वो स्पीकर के पास आते ही वो जो अभी खून से हो जाता है।
मुझे प्रॉब्लम नहीं है
नहीं तो थोड़ा सा आगे जाके देखो बस यहाँ से। और नहीं तो फिर वो कुर्सी के पास। हाँ, क्योंकि ये जो स्पीकर अभी जो चल रहा है उसमें मैग्नेट है और ये वायरलेस को बड़ा इंटरफेयर कर रहा है।
DPT
Probably the network is probably.
Yeah, yes, that's right.
अच्छा ये रजिस्टर ऑफ इसको देखेंगे दिन
ठीक है। रात को भी इंटरनेट आ गया था नहीं, सुबह तो ग्लिच था, मेरे जाने के आधे घंटे के अंदर रिज्यूम हो गया।
अराउंड 1 बजे तक बहुत हल्का आया उसके बाद फिर प्लान में भी चल गया इसको ओपन करिएगा।
वो कुछ किसी ने ना ग्रुप बना दिया मिला है फिर हॉस्टल। अभी वो हॉस्टल और ये सब बंद है, सिर्फ इतना पार्ट चल रहा है।
रडार में चल रहा है,
रडार में चल रहा है, घर तक चल रहा है। ठीक है।
हाँ
हाँ जी, किससे बात करनी थी?
This submission is today night and वो बोल रहा है सर आपका सिग्नेचर चाहिए वही ना लास्ट वन दिस किट्स are I think I'm now playing why am I going into the last report is have you seen the report? Yeah, I can send that. It's really nicely done. But one thing I was very much surprised from seeing the panel was many things which he has done and for which he is not so confident and having confirmation about. He has included. I mean, he is difficult to do in the sense not really very easy. If you're not convinced, it's not. See, like not asking for sending this for publication. For me, those guys will evaluate. Even if I give for me like after 60, even if I give very good marks, वो लोग presented by इतना time तुम्हें मिला यही किया. He's not. He has learned the programming, learned the coding, learned the theory, learned the process, learned the बढ़िया किया है. लेकिन that is not reflected in the code. As well as the same thing happened with that Bombay girl. So I think she's from Saviors. She also. അത് അവിടെ കൊണ്ട് കൊടുത്തിട്ട് അവരുടെ അടുത്ത് മേടിക്കുന്ന ലൈവായിട്ട്. Usually, I think between the weeks, between the depression and between the maximum. So that is the thing. But then that's a good question. Apparently, I see people doing the other also depending on the easily, I was telling you that like you see like what is the typical values which are coming, and then you cross check because rather than that, because you see mechanism is the what is that. For example, in the context of university, basically we say like emission is obviously coming from that expanding region which is and but then the absorption is coming from this compound which is again moving along the line of sight, but which means they are also moving, the other one also moving. Both are shifting into the system. So but you need a reference frame to calculate the system. If you are calculating with respect to this moving frame, the other moving frame, you will get twice. So if somebody say like this thing and then, but then the interpretation changes. If you are going to say like this absorption, you will say that will be the first system. Absorption is like it's coming from an expanding envelope. Then we say then you have to take the different bytes. If the absorption is from the stellar, then you even have to do that is a reference. So वो देखना पड़ेगा. I mean that's what I said. So we don't have a clear picture here कि ये क्या है. Right? I mean we ourselves are not so sure. Like even accretion also we say like okay, it's only about when we talk about let's say we say like okay, we are only developing quantum. Right? I mean so that's the first question. That is coming in emission. So we are seeing the magnetosphere like this. Right. Spool up kind of. Right. So geometry we cannot say because you see the intensity varies with that. So that way we cannot say. That's how basic. So the peaks. Yeah. So my suggestion is don't mention much about the values if you don't have it compared that with the standard model. But then you can say that primarily as an indicator of this. That is who goes something. So then we need to look further into those things and do. So always see to it like then people ask these things how this profile is formed and any profile. Always come up with the double beta and any profile. Always come up with the very simple interpretation. That's it. No what fancy thing maybe like maybe for me no speculation. No. Just come with the classic. And also see this bigger picture. For example, imagine somebody is asking you, okay, both of you and like we discussed last time. In general, like what you're working in. I mean, always try to see the basic paradigm, right? I mean, in the sense, for example, if you ask you need to specifically say like what is the thing we are looking at least in the context of this and trying to figure out how these lines are formed and the possible contribution to these lines. That's very important. And from there, you will be looking into the opacity related things. Why it is important? Because opacity affects the system as well as in the other contribution. So that way, if that distinction can be figured out, we can understand the system that which hasn't been. So you see that. And then, for example, if your project is somebody else, your intention mostly will be a general business or a business generally to be then we generally these questions. But then if you're looking into the bigger aspect, like, there are some open problems, like there is uncertainty about the mass of the relation with the mass, how they are capacity. Here we have a sample, even let's say, also regarding the acquisition paradigm we talked about, there is no like we have there's a matter there is the here being modified and being transformation. We need to diagnose and classically some of them are both. Our idea is to see, I mean, here in this discussion, we didn't use any sort of things. Probably use, let's say, the or distance. But then the more thing was given by that needs to be considered. And also, people always, for example, particular side of this what always ask like, so what do we think? All these things. And that's the integration. I think these days I don't know about it. Because we all went through that. That selling part comes from the point whether you have photo. Right. I mean, because you need to see the thing is you need to understand what you need to do. And that is the project. Because you see, one thing I really worry about these things, I don't want that much my colleagues. Getting that submitted. Okay. And then do I show. So don't fall for it. I mean, because these are the platforms you easily, because you submit them to the own page. You're explaining something or even some question. They're just shooting and you won't be there. You are limited. And then after that, music conferences. So, but then you have to see that because people are giving ideas to what I'm saying is not like blocking. That's the class we have to go. But then always should be having these things. You cannot challenge or you can challenge, but then you cannot outright sort of question I that is from a check. I'll tell you because you did even I cannot speak on behalf of you in if somebody asks me this year, it is a broader thing and everyone stuck. I mean, if I was being asked, I will give my comment. I would say like what is it for different we have usually the most the memory size is like one of these converted. I can see this but it's better. That distinction you can really see because from Singapore, they had already that initial mistake. That's why you see they have to come from the but then, if I happen to hear or over here, have a specific lack of confidence over these things from our group, I feel bad, and I may control myself not to ignore it.
Fresh.
No, no, we have not a problem for us. But then, in fact, we can try to keep. Yes, yes. Yeah, will you loaded your talk? Yeah.
Yeah. You are after me.
Huh?
I got the chair. Maybe I thought of ये सब cluster वाले लोग हैं तो फिर
Last hour. So anyway, you use your time. I request you. It will help me. Before. Very nice.
No, I don't think I.
Very nice.
But you came in 2019.
Publication.
So 2019 August में था.
Yeah,
You came in
yeah.
January.
With your group, yes, we've done. Yeah, lots of. Yeah, unfortunately, he could have published more papers, but what happened, he was involved in chemistry single-handedly. But nevertheless, that paid off. Yes. Actually, in the beginning, he wanted to leave astronomy and wanted to
Good afternoon, all. Good afternoon, all. So here I'm discussing about the stellar population in star-forming regions, in a few star-forming regions. So as we all know that stars form in molecular clouds, and most of the stars they emerge as cluster or groups. So these clusters contain stars of different mass. Depending on the mass, their evolutionary phases may be different. And so if there are like high mass stars in the star forming region, so when they form, they begin to ionize the surrounding molecular cloud and create the H2 region. And when this H2 region expands, so the expansion of the H2 region may induce the next generation star formation nearby H2 regions. So there may be different processes or different mechanisms which can trigger the star formation. And like here you can see in the first figure, so you can see the result of this kind of mechanism. This is called the radiation driven implosion. That if there are already some pre-existing core or clumps in the nearby molecular cloud, so they can be implode due to and form the next generation stars. So in this case, we can see the young stars which are aligned towards the massive star side or ionizing star side. And we can also see this kind of bright ring feature. So this kind of clouds, they are called the bright ring clouds. And similarly, we can also see this kind of morphology of the H2 regions. And in this case, this is called the collect and collapse. So we can find the massive stars or a group of low mass stars at the periphery of the H2 region. So here, when we study the massive star forming regions, we can use the massive star forming regions to study the premium sequence evolution of young stars, as well as we can also study the environmental effect of the massive star or radiation, radiative feedback on the ongoing or the next generation star formation. And we can also study the properties of young low mass stars in such kind of environment. So here, because already in the previous talks, a lot of introduction has been given about the H2 regions or the massive star formation. So here I am directly going to the one of the star forming region which we have studied. It is called the SS2112, and this is the optical image of the H2 region SS2112. So here we can see in the optical image that this blue color is basically the this is the CGBS emission. So here we can also see the dark cloud type thing around at the periphery of the H2 region. This is this symbol. This is the location of the massive star which has excited this H2 region. And when we go from optical to infrared, so we can see that in the infrared, here this is the massive star. We can see two regions, sub-regions where we can see a nebulousity, as well as there are a lot of young stars or red stars here at the periphery. So so it means that when we go from optical to infrared, we can reveal more young stellar objects in the star forming regions. And we identified the young star in this region, H2 region, using Euclid's data as well as WISE data. And this is showing the location of these point sources, green or cyan sources. Cyan points. They are the young stellar objects which are at the periphery of the H2 region. So from here we can see that most of the young stars, they are at the periphery of western periphery of the H2 region, while towards the eastern periphery we can hardly see any young stellar objects. And this circle is showing the optical extension of the H2 region, and here these black contours, they are the extension map for the region. So from here we can also see that most of the extinction, most of the VISOs, they are VISOs as well as this extension is contained towards the western periphery of the H2 region. So here in the longer wavelength, we can see that here we have shown with black contours, we have shown the spatial distribution of the young stellar objects. So we can see grouping of young stellar objects. So these groupings, they are showing the recent star formation activity in the region. And we can also see this is the GMRT radio observations, this magenta contours. So we can see that most of the ionized gas, this is contained in the western side only. And we also use the GMRT radio observations, and we could find one ultra compact H2 region here. This is these star and triangle symbols. These are showing the MSX sources in the region, and one of the radio contour, one of the peak we found towards this MSX source side, and so it indicates that this may be a very massive star here, and this has created the ultra compact H2 region. So we also calculated the spectral type of this probably massive star, and it comes out to be around 0.5. And then we also find an arc-like structure here in the southern periphery, and so from here we can also see that in H alpha also here we can see a rim-like structure here. So this is basically tracing the ionized boundary layer at the periphery of the H2 region, and here we also calculated the. And when we saw the CO distribution or molecular cloud distribution in this H2 region, western side of this H2 region, so here we can see there are this is tracing the CO emission and molecular cloud in the western periphery only. So from here we also calculated the ionized gas pressure inside the IBL and also the internal pressure of the cloud. So the pressure inside the cloud was less than this IBL pressure. So from there we conclude that whatever star formation is going on inside this molecular cloud, it may be triggered due to the expansion of the H2 region or due to this massive star which is here. So from here, we studied the triggered star formation scenario in this S2-112 H2 region, and we conclude that the expansion of the H2 region has triggered the star formation in the western periphery of the H2 region. So basically, this H2 region is bounded only towards the western periphery, where is most of the there is a very less material towards the eastern side. So other observation that we can do with the star forming region, we also study the initial mass function, and with the recent with the current high sensitivity observations, we can very well detect the low mass stars in the star forming region or clusters. So the like here, this Osorio et al. They have studied the sigma Orion cluster and detected very low mass stellar and substellar mass object in this sigma Orion clusters. And there are other there are other regions also where this stellar to substellar mass objects are also studied. So this ratio, stars to brown dwarf ratio, it is also used as a proxy to determine the shape of the IMF. So here for different star forming region or cluster, which are not very far away, means within one kpc. So this ratio has been determined. So we can also study this shape of the mass function for the low mass end, or by studying the stellar to substellar mass objects ratio in the other clusters. So here we have used the Young cluster Berkeley 59. So this is located in one of the H2 region, which is called SH2171, and it already this is a Weiss image of this H2 region, and we can see there are many young stellar objects in this H2 region, and here the main cluster is lying here, Berkeley 59. So it has a very good number of young stars. So we studied this cluster using deep optical and NIR observation using NICS and Dolores instrument mounted on 3.6 meter PNG. And from that, we have also got a sample of young stellar objects which were obtained using the SPITZER as well as X-ray observations. And we found the optical counterparts of these young stellar objects in our optical data, and most of them were showing ages between 1 to 5 million years. So using this deep optical data, we could detect the stars up to 0.2 solar mass, and we also studied the initial mass function for this cluster in the mass range between 0.2 to 28 solar mass. And from that, we found out that it's similar to other galactic clusters. The mass function slope is minus 1.33 plus minus 0.11. So we didn't find any environmental effect on the mass function of this cluster. And when we go from optical to infrared, so we can see that we could detect the stars up to we can detect stellar or substellar sources up to 0.03 solar mass. So this is a very deep photometry till date for this cluster. And we also calculated the stellar to substellar mass objects ratio for this particular cluster, and it turns out to be around 4, similar to other clusters which are shown earlier. And so now I am showing some results which are based on the 3.6 meter dot observations. So this is the one of the cluster, NGC 1893. So these deep optical observations were taken with the imager, and here we can see this is the NGC 1893. It has many massive stars, and it has due to its expansion, there are two cometary globules which were formed, SIM 129 and SIM 130. So basically, we focused on this central cluster, and we took the deep VI observation with the imager, and we also found the kinematic members based on the Gaia ADR3 data. So here, this is the CMD which is constructed using the dot data, and here these dot sources, these are basically the Gaia members, and we can see that based on the Gaia data, we could only find members stars up to only around 20 solar mass, 20 magnitude, and So to find the cluster members which are fainter than this, we did, we use the YSO sample, and these are the optical counterparts of the young scalar objects in this cluster. So we can see here that with this data, optical data, we can detect up to around 25 around 25 magnitude stars, and using this, we could construct the initial mass function for this young cluster, and we found that its slope is similar to other open clusters. Then this is one of the Bright-Rim cloud, which and this is taken from Ogura et al. 2002. So this is these are the H alpha stars in the region, and this region is situated around at around 900 parsec scale. And here we can see the hierarchy color composite image of the same BRC. And we can see that here we can see a grouping of like many H alpha sources, and this is also prominent here also. And so we took TCAM2 observation for these 3 subregions which were covering this basically this elongated cluster, and from this this data, TCAM2 data, we could detect the stars up to around 20 around 20 magnitude, and this corresponds to around 0.03 solar mass. So with using optical and infrared data, we can detect a very low mass stellar as well as substellar mass objects in the nearby H2 regions or star forming region. So yeah, I just wanted to show that how much speed this can go, and we can detect substellar mass objects also, and we can again reduce the shape of the mass function towards the very low mass. And so that's it. And this is the summary of
Just curious about TCAM2, what was the total exposure time, and this is 10 sigma magnitude?
yeah, this is 10 sigma. And total integration time was around 500 seconds.
Good talk. So your measure, what is the field of view of individual frames?
It was 6 by 6 hours.
But
So I have taken only 6 by 6 hours minutes, a central portion of that cluster.
And you have the full filter set off, but you are using only V and
V and I, because I wanted to go very deep, and I didn't have much time.
So how much was the exposure time for this work?
It was 1 hour in each filter. Not 1 hour in V filter and 45 minutes. So yeah, but during that night, the night was very excellent. The like seeing was around 0.5.
Okay. Good. Thank you.
So we continue. Yeah. Next speaker, Dr. Priya Hassan. You have 15 minutes.
So thank you. And so I'll be talking about the kinematics and structure of circuits. And this is work done in collaboration by students as well as collaborators. Light again. Oh, okay. Yeah. So next. Yeah. So the surface molecular cloud was detected way back in 1976, the 2-micron survey, and it's a very ideal cloud for studies of very young low mass stars and substellar objects at a close distance from us. And it has been very well studied. It's one among the 3 star forming regions after Taurus and IC348, which has a very good unbiased data set. And it's one of the most active star forming regions within 500 parsecs. And but the problem is it's challenging for membership analysis because the region is seen against a crowded background. And what you can actually see is this is the region. This is from paper by Rcw. And so what you can see is that there's this Aquila rift, which is behind, which is at a distance of about 600, 700 parsecs. The Serpent Cirrus is in the foreground, which is over here, marked over here. And this is the Serpents, which is at about 400, 500 parsecs, somewhere in between that. Now, what I'll be talking about basically is the Serpents main region. You have the Serpents northeast, and the far south, which I mentioned over here. And I'll be focusing basically on this, the main region, which is located over here. And yeah, so so what we're going to basically do in this work is a study of the YSO, the young stellar objects in this region. And now, since we have Gaia, the wish list is actually to have good astrometry as well as kinematic information with which you can identify cluster members and get astrophysical parameters from that. So we use the Gaia data for our YSO set so that we can, yeah. So what are we basically going to do in this work is that we're going to create a YSO sample using infrared, X-ray data, and various other data sets which I'll talk about. Cross-match it with Gaia EDR3 data, get the parameters. We use that to actually make a control sample and then query the EDR3 data in a 2-degree radius. And then what we do is we use machine learning techniques. There are 3, these are 3 clustering algorithms. One is called DB scan, optics, as well as HDB scan. And we use this to actually increase our membership database for this region and plot it on extinction map, get parameters, and identify the YSO classes using 2MAS as well as WISE. So the YSOs are detect. Oh God, the images have not come. Yeah, I think it's okay. This one. Most people know this about YSOs, but yeah, they probably do. Yeah, that's. Okay, then we proceed with this. Okay, so in short, this is the data set which I'll be talking about, which has okay, we go to the next one. Okay, so the first data set I'll be using is Serpents data with C2D data, which is there for an area of about 0.89 degrees. And the C2D basically studied 5 star forming clouds, of which Serpents is one. And this is the C2D data, which basically we have 286 candidate YSOs from the C2D data, which is from Harvey 2007. Along with that, we also used another data set, which I've worked with in the past, which is the Flamingos data set, which is using the Flamingos detector of the on peak. And this basically was an earlier work we had done, where we had, you can see the footprint, or this is the C2D footprint, and the Flamingos one is the blue one, which is around it. And basically what was done is 17 fields were studied in GHK bands using the Flamingos data set. And that's the data set. And we identified the near-infrared YSOs, plotted them over here. This is earlier work done by me, where we actually then identified clusters. There were clusters in this star forming region. But these are with YSOs without verification in terms of membership. This is just using their infrared signature. So we use this data set as well as use X-ray data by Winston, but Winston is only there for the core, the surface core region, which is which is where cluster K is. That's the core region. So we have X-ray data only for that region. And then there's the data set by Spetzi et al., which is basically R-band, Z-band data, which was over the C2D survey to cover the same region. So this is the whole YSO sample which we've used. Spitzer, the infrared excess ones, the X-ray by Winston, as well as the Spetzi. So we have 656 unique sources. And we also matched this with another paper which is there, which actually identifies members using DR2 data for the surfacing for this very large region. It's almost 32 by 26 degrees field. And with this paper actually identified kinematic members. So we cross-matched our YSO sample with this one. And we also cross-matched our YSOs, 656 YSOs with EDR3. But you can see that if you take it with these 87 sources, which were there with the confirmed members, that's the green ones, the green set. The cyan one, what you can see is the cross-matched sample, which you can see that obviously there are some of those which are non-members. And the red one is if I put cutoffs for the matched samples, then I have the red one, and that's this thing. But to be sure about the values, I stuck to these 87 sources with which we got values for the distance, proper motion RA, proper motion depth. Now, what we did is then we actually queried the Gaia data sample within a 2-degree radius using cutoffs which were there identified by that control sample, as well as certain quality cutoffs like these other factors for the RUWE and the errors, etc. So we basically got the data for that mistake. Now, in machine learning, we can use various techniques. There are supervised techniques as well as unsupervised techniques, which you can use for this kind of work. We had done earlier work with supervised learning, where we actually did membership of stars using random forest. But this was actually using cluster member data sets, which were given by this reference of Cantor-Gordon 2018, which actually identified members using, and we used that and then used random forest to get members. What we did in this case is that since we do not have such a member list for this, we actually use clustering techniques of machine learning. These 3 clustering techniques, DB scan, optics, HDB scan, they have the advantage as a density based. They have the advantage that you do not need to know the shape and number of clusters. You can estimate the densities and pick up regions of high density. So that's what we did. So DB scan works on a very simple principle that, for example, if this is the thing. If you have a star, you make an epsilon radius around it. If you have minimum points 4, if they fit in, you say it's a 4 point. You look for the next one. If it has with an epsilon radius minimum points, it becomes a 4 point. For example, this point, which does not have, it falls in the region, epsilon region for this star, but it does not have its own minimum points. Therefore, this will be a border point, while the other ones will be noise points, right? So using this, we can identify, density points for people for different sources. And you can get it in a plot of this kind. Depending upon the threshold you put, you will be able to identify clusters. So this is something like islands in the ocean. So you, depending on the sea level, you can actually identify different sets of clusters. But the problem is, how do you identify, where do you put the cutoff? So optics is what is used to actually get the epsilon values. This is like a DB scan where you're actually using variable values of epsilon. So for example, if you had this kind of clusters, you have different values. These are different cutoffs, which will define how many clusters you get. So for example, if you take epsilon 0.5, your cutoff will come here. You'll only get these 3 clusters. If I make epsilon 2, I'll get all these. And it actually optimizes it to the ideal value to get. Along with this, if you have variable densities, there is something called hierarchical DB scan, HDB scan, which will actually be able to identify it with variable densities. So we used all these 3 methods. With DB scan, and by the way, this is in 5-dimensional space, which is X, Y, Z, PMRA, PMZ. And using that with DB scan, we can identify our members over here. This is the optics plot which we have for it. And you can see that in X and Y, it comes something like this. In proper motions, you can see you get this main cluster and this. Now, how do you identify which are the members? So again, we used the earlier paper, which I had mentioned over here. And over here, this has already identified that the serpent star forming region has basically this values, while the backgrounds coming from serpent south as well as northeast, etc., are this region. So that's what we used to identify that these are our, the core members. These are the background ones. So when we do DB scan, these are our values for proper motion. These CN points are the members we get, which we plotted in velocity plots, and everything seems fine. We also used HDB scan. HDB scan, because the variable threshold, it can uncover more clusters. So we actually got 2 clusters, which HDB scan, which are plotted over here. And yeah. So now with the clusters that we have from HDB scan, we could identify our 2 clusters. This is the larger one, which has 305 members, which gives you a revised value for the parallax, the distance to be 446 parsecs, as well as the proper motion in the proper motion deck. The second cluster has a distance which is slightly further away, 462 parsecs. But it has similar values for the kinematics because they all finally belong to the same cloud, and hence there is the kinematic signature still there. So this is the HDB scan members which we have on the extinction map. The extinction map was found using NICER, and you can see the members plotted over here on the NICER map. We plotted them on color magnitude diagram. Yeah, okay, I'm almost done. We cross-matched now for the Y source. We classify them. We cross-match them with 2 mass as well as Ys. And with that, you can see that these pink stars are my class 2 members. Class 3 are over here. These are the and obviously, in this kind of method, the problem is we can't get class 0, class 1 because Gaia will not see them, right? They would be too extincted for Gaia. So we only get the class 2 and the class 3 sources in this case, which are shown over here, where class 2 is pink and class 3 is the gray. And these ones are the So those are my results. So what we did is we actually have now a bigger sample of YSO confirmed members using the data, using machine learning techniques. And that's our results where we classify this new set of YSOs using these techniques. Thanks.
So once you have identified the cluster, so many members, what is the next? What is the physics you looking for?
Yeah, so one thing is you can redefine the members using the parameters, right? Like which I showed you, the proper motions, the parallax, and things like that, for a larger sample. Because otherwise, if you just have 87, it's less. And then you can classify it like I did with Ys and 2 mass. You can classify the YSOs. Get the distribution.
No, that is okay. But
yeah.
I'm asking what is the next? Means what kind of physics are you looking for?
Yeah.
Because this is well studied region.
Yes.
So
yes.
I'm curious to see what kind of physical process you are looking for. Once you get a more members, more clusters. So
correct.
Is there any physical process you are looking for to explain those clusters?
I think that then one would actually, because the problem, the problem with Gaia is that because it's an optical bands. So with YSOs, it doesn't work so well. So probably this would be good to get your samples of disk-like stars, etc., to actually then do follow-up observations on them. So you can build up samples which you can use for further investigation. Actually, that was what was the plan for, in the sense for 3.6. That with this you can now pick up confirmed stars which you have more confidence on, for which you can do spectroscopy.
Yes. Yeah. Yeah. So this matching, cross matching you to different images. How do you actually resolution this machine learning? This automatic.
No. So what we do, the cross matching actually, Gaia ADQL has a smart way of doing it. It's not just direct matching. So if you use the Gaia, the query, this thing, they have a smarter way of doing it because you need to do it with resolution. So it's not just the closest. Yes. But that is a tricky problem.
Can you show the parameters of both the clusters?
Yeah.
The distances are quite similar.
Yeah,
right? I mean,
that's right.
And the other values are not given there. I mean, is it quite possible that both are like similar plus same cluster?
Yeah. So actually, that's the thing. The DB scan sees it as only one. when I run DB scan only sees it as one big chunk. What HDB does is that it does it at a smaller level. So in principle, they are not very different. Because you see the distance only, there's a small difference. Yeah. Yeah. So it's not much. It's not much. Yeah. Because if you see the errors, yes, it's not much. So, but just that since it gives, and even there are only 20 members. But ideally, for different regions, probably it could give you a better, better substructures. In this case, it doesn't, because this seems to be one big chunk only. Achha. I try to stay as far as possible.
Sorry. Yes. So this is for the presenters who are presenting here. Actually, this presenter also creates interference with the radio. So one has to just separate all these two along with this speaker. So make a distance from the speakers, and these two should be separately used as the interference. How much? Just no. Actually, this has to be in the back pocket. So the speaker can stand here, right? And this continuous noise and interruption can be minimized. Okay. Thank you. Thank you. So you can speak here. That will be better, right? We have a 30 minutes. Good. 12 minutes and 3 minutes.
Hello, very good afternoon. So I will be talking about star formation in star clusters and cluster regions. So this is the outline of my talk. So at first I will be introducing the topic, and after that some of the important findings that I got after carrying out this study of some of the star formation. And finally I will summarize my talk. So starting with the young star cluster. So the young star cluster basically are the clusters which have age less than 10 years of course. So they are basically embedded in their parental molecular cloud. So here I've shown a color composite, GSK color composite image of a young star cluster called NGC7538. So here you can see the bright stars here, which are visible in optical cave. Simultaneously, you can also see the significant amount of embedded population in this region. So the most of the members of these young star clusters are in premium state, while they may also contain different stars, giant stars and various stars also. So now the massive stars which are found inside these young star clusters or nearby them, they deeply affect their surrounding molecular material. So the effective temperature of these massive stars is greater than 50,000 Kelvin. Luminosity lies from 10 to the power 4 to 10 to the power 6 solar luminosity. So we have shown a HR diagram. So you can see here the massive star lie at the top left corner of this HR diagram. So these massive stars by analyzing their surrounding molecular material create the astro region. So the astro regions are basically the emission nebulae created when these massive stars ionize nearby gas cloud with high energy ionization. So I have shown a cartoon diagram showing astro region. So here you can see massive star sitting at the center and irregular shape kind of structure can be seen here. So various kind of recombination lines like H-alpha lines are produced by this astro region. Now the expansion of this astro region in the surrounding material trigger the star formation there. So now there are quite two popular models which have been proposed to explain the formation of star formation process in the nearby of the astro region. So first one is the radiation-driven implosion model. So in this model, what happens when the radiation from the massive star interacts with a pre-existing molecular clump. The implosion of this clump leads to the formation of the stars, which is known as the radiation-driven implosion. In collect and collapse model, what happens when the ionization front from the massive star passes through the surrounding homogeneous molecular material? So what happens as the this front ionization front passes through the cloud, soft gets generated. So at the accumulated material between these two fronts, like soft front and the ionization front, lead to the formation of stars. So here I've shown a cartoon diagram representing this collect and collapse model, and here I've shown cartoon diagram representing the implosion model. So these are the observational signatures, like the PRC are the quite good example of the radiation implosion model. While in the collect and collapse model, you can see the collective material layer of material around the massive star. So these are known as the observational signature of these two processes. Now the formation process of massive star is less understood as compared to low mass star, because they are rare, they are deeply embedded, and their initial evolutionary phase is short-lived. So the models like core accretion, comparative accretion is there, but the two models like half filament system and cloud star collision are quite popular in explaining the massive star formation. So here I've shown a cartoon diagram representing a web kind of structure. So here you can see that these filaments are entangling at this point and creating a hub kind of structure. So this is known as a hub, and these are the filaments. In this diagram is showing a cartoon diagram representing cloud collision model, where the two clouds are colliding with each other. Now the Kumar et al. 2020 explained the formation of massive star through this filament system as a four-stage process. Now in the stage one, you can see that these filaments are approaching each other. When they interact with each other, they creating kind of structure. And when the core gets formed in that hub, and when the fragmentation of core leads to the formation of massive star. Now this massive star can ionize their surrounding material and create the S2 region. Now this is one. Below is the cartoon diagram representing the cloud collision model. So here you can see that two clouds are colliding with each other, and the compressed layer between these two clouds are compressed layer is leading to the formation of the massive star. So these two processes are quite popular in those days. Now in the next few slides, I will be taking showing some of the results which I have got. So this one the known as the Southwest region on the S2 region. So this is also known as the Rcw-42 S2 region. So there are three massive stars in this region: 207, 208, and 212. 207 is a co-type star, while the 208 and 212 is B-type of star. So here we perform surface density analysis in this region, found the clusters, northeast cluster here. So these surface density contours are shown here in this image. So here you can see the cluster is there, and northeast cluster, we call this cluster as northeast cluster. So we perform the basic cluster analysis work in this region, like determining the age of this cluster, radiating distance toward this region, also using the optical data and photometric data and acidity data, near infrared data. So I'm not talking about that thing, but I will focusing on the star formation thing. So this is these four images are showing the morphology of Southwest S2 region. So here this image is color composite image made using the 22 micron, 12 micron, and H alpha images. So here you can see the H alpha with the blue color, and the arc kind of structure can be seen in the 12 micron. So here we have also overcoated the Y-axis here. So in the second image, 160 and 60 and H alpha image, you can see similar kind of structure where you can see a cocoon kind of structure. So S2 region is bounded by the gas and dust from the one side, while the other side of the S2 region seems to be devoid of gas and dust. So this in this Atari 160 micron image, which is overcoated with the Planck image, you can see gold dust distribution. So here you also see these massive stars. It seems to be lying at the boundary of this S2 region. So this kind of morphology we call the crystal morphology, where massive star is fixed at the center, at the corner of the molecular cloud. So in this image, I have shown few of the things like this green contours are representing the 21 centimeter nuclear hydrogen contour, from the past. These cyan color contours are the NSS radio continuum contours. These blue colors is showing the extinction contours, while these red color is showing the surface density contours. So here you can see that there is a dense gas material between this massive star and this cluster. So this kind of morphology we have seen in multiple of S2 regions. So from this morphology and the signposts of triggered star formation, like their age gradient and the pressure calculation, we suspected we found that the triggered star formation process may be possible in this region. So here I have shown a high resolution radio continuum image of this region. So this is the NVSS radio continuum image, while this is the radio continuum image at 1280 megahertz obtained from the GMRT. So you can see that the 1280 megahertz radio continuum image has a better resolution and is showing the morphology of this radio gas distribution. So here you can see that the massive star, the radio gas distribution likely in circular kind of structure around this massive star. The ionization, this ionized gas is interacting with this black contours, which is the 12 micron emission. So this is the kind of radio morphology we got in this region. Finally, we also inspected the massive star formation process in this region by examining the mid-infrared and far-infrared images. So you can see I have shown a color composite image of this region using the Planck 870 micron image, 160 Akari image, and 22 micron image. And so in this image, we found that there are filament kind of structure which are joining it at the center, where is the massive star formation is there. So we suspected that there could be possibility that there may be a filament system in this region. So to further explore this hypothesis, we need a high resolution CO data, but unfortunately we don't have that data, but will be explored in further analysis. Now I am showing some of the results from another object, which is okay. So this is the Sarpless 193 complex. So here I've shown color composite of this image. So these white contours are the radio continuum contours, and these clusterings which we identified in this region. This is the Herschel 500, 160, and HL5 image. So in this image, we have found this P1 and P22 clumps are there, and we have also found the clumps in this region using the Herschel column density map. We have further analyzed this region using the JCMP molecular data. So we found two peaks at this region, which is where we have found it that clump P1. So we with this spectra we have found the two molecular velocity components there. One is from -40 to -43 to -46, and another one is from -47 to -50. So these two cloud components are shown in this image with the yellow and brown contours. So it seems that there is a two clouds in this region which are entangling at this point P2 and P1, where we have also seen the presence of Y source and the cluster. So it may be possible that the cloud collision process might be responsible to form this region stars and this cluster. So this RG image also shows the same fashion. We have also extracted the position velocity diagram along this x1 x2 axis. We found that two velocity component in this region, this one and this, and these are connected with each other. So from these observational evidences, we have suspected that the cloud collision process might be responsible for the formation of the stars in this region, massive stars in this region. So finally, I am showing some of the results from this region. This region is known as the Sarpless 261 region, which is a compact S2 region. So it contains a star S0. So it is here we have shown a color composite image of this region. We are using 22 micron, 4.5 micron HL. So this image shows the morphology of this region. So so there is an infrared cluster in this region. So we image this region with the DCAM2 observation. So these are the detail of the observations. So this is the final K-band image we got after cleaning, aligning, and then average to get the final image. This one we performed the photometric data reduction in this image using RF like PSF42 and all. Finally, we calibrated the magnitude to the instrumental standard magnitude. So what we found, we are going up to the 18 magnitude in the K band. So we have further analyzed the molecular velocity kinematics of molecular in this region using GSM big data. So this is the spectra I got in this region. So this is the movement zero map. So you can see that this one is the 61 region. We have found another region which is known as the Rationale-502, which is a ultra compact S2 region. So we know that the ultra compact S2 regions are the initial tracer of the massive star formation. So these results are pushing us to examine this site to explore the massive star formations again.
So, sorry, question that is good. Was that for telescope or Filament?
This
Yeah.
From Filament.
Oh.
Rakesh, did you, in second region, you have shown that position velocity diagram, you are seeing two components. So have you checked whether are there really outflows or some collapsing out? It could be outflow. There is a high possibility.
I have not examined that, but yeah. So these are the initial regions. Yeah, okay.
Just explore it.
Yeah.
Okay, let's again speaker. Let's drop. So you have 12 minutes. Okay, I'll change party.
Good afternoon, all of you. I'm Harminda from my university, and I'm working I am working with Dr. Saurabh at Aries and Dr. Alok Dugapal at my university. Today, I'm going to present a talk on physical environment of young star clusters. This is the outline of my talk. First, I go with the introduction in which I briefly describe for young star clusters and importance of young star clusters, and then I'll go for analysis and then summary. This is a typical example of young star cluster NGC 3603. This is in this picture we can see that at the center, we can see that there is a prominent main sequence and pre-main sequence stars of this cluster, and we see that some dense star clouds are present in this star forming region. These sites are most probably star formation sites in future, and we see some young stars, pre-main sequence stars present in this cluster, which are still embedded in the present nebula, and we also see that some aging supergiants are also present in this cluster. What is the importance of the study of young star clusters? As we know that young star clusters have aged less than 10 million years, and they are the laboratory to study the recent star formation, as they are just formed from the gravitationally bound molecular cloud and still embedded in the parent nebulous region. And these clusters are considered to be the fundamental sites of the star formation in our galaxy. Clusters also constitute a principal link between the theories of stellar evolution and observable universe, and hence provide information on galactic evolution. As young star clusters, stars present in the young star clusters have same age and the chemical composition, but they are only different in their mass. So star clusters are excellent way to study the effect of mass on stellar evolution. And spectral distribution of open star cluster in the galaxy define the spiral arm of the galaxy. These are the data sets which I used in this work. This is the overview of the second region which is under study. And this is the color composite figure of second region with 22 micron, 12 micron wise and 2.17 micron of 2 mass K band. And these green square boxes are the cluster regions which I use for analysis of clusters. And this whole 1.5 into 1.5 degree field of view is the over region which encloses these 4 clusters. And these young circles are the young stellar objects which I found in this region. These biases are from WISE and near infrared data, because we didn't have that mid infrared data in this region. Now I calculate the spectral structure of the clusters. To study the structure of the selected clusters, I use stellar density maps for the sample of the stars taken from the near infrared catalog, which I used to mass and plus combined with UKET's survey. Fainter stars are taken from UKET and brighter are taken from TUMAS. And the stellar number density maps are generated using the nearest neighbor method as described in the Gutamut et al. 2005. And the lowest contour is 1 sigma above the mean stellar density, and the step size is equal to the 1 sigma. We refine the definition of cluster area using the convex hull. Convex hull is simply a convex hull of a set is simply a convex polygon of a data set which encloses all the points on it. And rather than the circular area around the objects, as the later method tends to significantly overestimate the cluster region. This is the convex hull of first cluster, Waterloo 01. The stellar density contours are shown in the black contours, and that purple and green curves are the convex hull of this one is purple one is for cluster region and green one is for core region. Cluster is basically a lowest density contour, and core is region within the half of the peak value of stellar density. And this one is for sharpness 208, and this is for sharpness 207, and this is one star forming region present in our field of view, that is 2 mass XJ 04183258. And we estimate the cluster area using the Q hull, which is area of cluster is equals to area of hull upon 1 minus n hull upon n total, where n hull is the number of vertices on the convex hull, and n total is the number of objects, and a hull is the area of the convex hull. As convex hull by itself tend to be smaller than the true sampling window, so to be consistent we define the R cluster as the radius of the circle with the same area of the cluster. These are the structural parameters of the 4 clusters, and For data completeness, I use Penstar data for all the 4 clusters, and photometric data may be incomplete due to the various reasons. So we have to check the completeness factor of the data. To determine the completeness factor, we use the add star routine in Dalford second, and the threshold detection was chosen such that the detections are similar to the Penstar catalog, and the instrumental magnitudes are then converted to the standard magnitude by applying offset determined by the PS1 catalog. Now, to study the structure of the cluster or reliable membership, like based on the proper motion studies is required. So I use Gaia idea 3, early data release 3 for membership probability. And for this, I use this method to calculate membership probability of all the 4 clusters. And we took Gaia proper motion data located in the convex hull of all the cluster regions. I used to determine for membership probability of the cluster. This is the in upper panel. This is the proper motion vector point diagram. Is shown for Waterloo 01, because Waterloo, out of all the 4 clusters, Waterloo is the only cluster which show more clustering than all of the 3 clusters. Sorry. In this subpanel, we can see that that white dots are the stars present in the convex hull of the cluster, means inside the lowest density contour, and this prominent clump, which is and its radius is around 0.5 milliarcsecond, and we can easily distinguish between the field star and that prominent clump. The stars present in this clump have most probably the same proper motion, and they are the most probably the member stars of the cluster. And this is the G versus GP minus RP color magnitude diagram of the same region. Like this is for whole cluster, and this is for clump, and this is for field region. This is the estimated membership probability, and the proper motion errors and the parallax are plotted with the as function of G magnitude. Here we can see that proper motion percentage membership probability of is greater than 80% are up to 20 magnitude, and as the proper motion error goes high, the membership probability becomes lower, and at the lower pentatime we can easily distinguish between cluster and field star. This is the color magnitude diagram, G versus G minus Y CMB of Penstar data for the Waterloo 01 cluster. Here, black one are the cluster, all the stars present in the cluster. Green one are the probable cluster members, and red one are the wire source. And this red isochron is the post main sequence isochron corrected for the extinction 2.21 max in AV, and it's corrected for the distance of 3.24 kpc. These are the distance and reddening parameters of all the clusters. We use Ballard-Jones approach to calculate the distance, and we also combined it with the isochron fitting analysis, and these are the distances. And this is the reddening of all the cluster, which I used from the Green et al. 2019, and from this we calculated AG and AV of all the clusters present in the region. This is the summary and the future studies, as we don't have MIR picture data of this region. This is the W4, W3 and 2 mass K-band image, and it's overlay with the NVSS 1.4 gigahertz contour. We can see that it's a loss of clustering in this region. This is a bubble kind of thing, and in this study we we studied that out of the 3 clusters, we have 3 clusters which have elongated morphology, and the literature suggests that these clusters have low metallicity clusters, and their proximity in the sky, like this is Waterloo, this is sharpness 208, 207, and 2 mass day. They are all on sky position. Their proximity in on sky position and identical metallicity suggests that they are maybe in the similar environment. In future, the combination of these 4 clusters may enable a unique study to the evolution of initial mass function and the stellar star formation in the region. And our aim to study the IMF in the region in with the different population, because out of these 4 clusters, they are from different age, as literature suggests, and how star formation is going on in this region. Thank you.
X is EB minus 1.
Yeah.
Did you find any variation or almost stable?
No, sir. Actually, I used that Green et al. Relation in extinction relation equations, and they are quite different with which we use for optical VBRI in Telestar.
Okay, thank you. Let's thanks on speaker again. So we meet again 3:45. Next, after tea break, we have a 4 talks, and chairman will be Dr. Manohar. So he believes that we have a 5 o'clock colloquium is there, so time has to